At the center of a distant galaxy cluster lies an object that challenges conventional definitions of what a galaxy is. IC 1101 is an ultra-giant elliptical system whose scale exceeds that of ordinary galaxies by an order of magnitude. It exists not as a sharply bounded structure, but as a vast, diffuse accumulation of stars extending millions of light-years into intergalactic space. Observations indicate that IC 1101 spans between 4 and 6 million light-years in diameter. The Milky Way, by comparison, measures roughly 100,000 light-years across. IC 1101 is therefore not simply larger, but fundamentally different in scale, with outer regions so faint that their boundaries are difficult to define. The galaxy contains an estimated 100 trillion stars. At its core resides an exceptionally massive supermassive black hole, likely tens of billions of times more massive than the Sun. IC 1101 is not thought to have formed in isolation. It is not an anomaly. It is an endpoint, a record of what gravity can build given enough time. When William Herschel found a fuzzy blob, the discovery of IC 1101 did not happen with fanfare or headlines. There was no eureka moment, no sudden realization of having found something extraordinary. Instead, it began on a relatively ordinary night in June 1790, when a German-born British astronomer named William Herschel was methodically sweeping his telescope across a patch of sky in the constellation Virgo. Herschel was already famous by this point. 9 years earlier, in 1781, he had discovered the planet Uranus, the first new planet found since ancient times. That discovery had transformed him from an amateur musician who dabbled in astronomy into one of the most celebrated scientists in Europe. King George III had granted him a royal pension, allowing him to devote himself entirely to studying the heavens. And Herschel took this opportunity seriously, embarking on an ambitious project to catalogue every interesting object he could find in the night sky. On June 19, 1790, Herschel's telescope, a reflector with a mirror about 18 inches across, swept across a faint smudge of light in Virgo. He noted it carefully in his observing log, recording its position with precision. To Herschel's eye, it appeared as nothing more than a nebula, a term astronomers of that era used for any fuzzy cloud-like object that was not a star. He had no way of knowing what he was actually looking at. The technology to measure cosmic distances would not exist for more than a century. The scientific understanding that separate galaxies even existed would not come for 130 years. Herschel simply saw a faint, diffuse patch of light, dutifully recorded it, and moved on to the next object in his systematic survey. He could not have known that this unremarkable fuzzy blob was actually a cosmic titan containing 100 trillion stars sitting over 1 billion light-years away in space. The object Herschel discovered that night eventually received the designation IC 1101. The IC stands for Index Catalogue, a supplement to the new General Catalogue of Nebulae and Clusters of Stars compiled by astronomer John Dreyer in the late 19th century. The number 1101 simply indicates its position in that catalogue. It is perhaps the most boring name imaginable for the most spectacular galaxy we have ever discovered. But in the 1790s, and indeed for most of the next century, no one had any idea that IC 1101 was anything special. It sat in catalogues as just another nebula, one of thousands that astronomers had documented but not understood. Throughout the 19th century, astronomers occasionally observed IC 1101, but their observations revealed little. Even the best telescopes of the era could only show it as a faint, fuzzy patch. There was no way to determine its distance, no way to measure its size, no way to understand its true nature. Some astronomers suspected that these nebulae might be island universes, separate systems of stars far beyond our own Milky Way. The philosopher Immanuel Kant had proposed this idea as early as 1755, but it remained speculation, impossible to prove with the instruments available at the time. Other astronomers argued that nebulae were simply clouds of gas within our own galaxy, unresolved, because they were too faint or too diffuse to show individual stars. The debate continued for decades with no resolution in sight. The technology gap between Herschel's discovery and actual understanding of IC 1101 was enormous. Herschel's 18-inch telescope was a marvel of its day, hand-ground and polished with incredible skill, but it gathered only a tiny amount of light compared to modern instruments. Photography had not yet been invented, so all observations had to be made by eye, with astronomers sketching what they saw or simply describing it in words. There was no spectroscopy to analyze the light from distant objects, no understanding of redshift, no knowledge of the expanding universe. Astronomers could measure positions in the sky with great precision, but distances beyond the solar system remained almost completely unknown. The nearest stars were known to be very far away, but exactly how far was uncertain, and objects like IC 1101 were so distant that no measurement technique of the era could even begin to gauge their remoteness. It was not until the early 20th century that the situation began to change. Larger telescopes came online, including the 60-inch reflector at Mount Wilson Observatory in California, completed in 1908. Photography became standard in astronomy, allowing long exposures that could reveal details invisible to the human eye. Spectroscopy developed into a powerful tool, letting astronomers determine the chemical composition of stars and measure their motion toward or away from us. These technological advances set the stage for a revolution in our understanding of the cosmos. And IC 1101, that faint fuzzy blob first seen by William Herschel in 1790, was about to be revealed as something far more extraordinary than anyone had imagined. The first hints came when astronomers began measuring the spectra of nebulae like IC 1101. When light passes through a prism or diffraction grating, it spreads out into its component colors, creating a spectrum. If the light source is moving toward us, the spectrum shifts slightly toward the blue end. If it is moving away, the spectrum shifts toward the red end. This effect, called the Doppler shift, is the same phenomenon that makes an ambulance siren sound higher pitched when approaching and lower pitched when receding. In the early 1910s, astronomer Vesto Slipher began measuring the spectra of spiral nebulae and found something shocking. Almost all of them showed substantial redshifts, indicating they were moving away from us at tremendous speeds. Some were receding at hundreds of kilometers per second, far faster than any star in our galaxy moved. This was the first clue that these objects might not be part of the Milky Way at all. The breakthrough came in the 1920s when Edwin Hubble, working at Mount Wilson Observatory with the newly completed 100-inch Hooker telescope, turned his attention to the Andromeda Nebula. Using a class of stars called Cepheid variables, which pulse in brightness with a period related to their intrinsic luminosity, Hubble was able to calculate the distance to Andromeda. The result was stunning. Andromeda was roughly 900,000 light-years away, far beyond the boundaries of the Milky Way. It was not a nebula within our galaxy. It was an entire galaxy of its own, an island universe, just as Kant had speculated nearly 2 centuries earlier. Hubble announced his discovery in 1925, and astronomy was transformed overnight. The universe was suddenly far larger than anyone had imagined. With this new understanding, astronomers began to look at objects like IC 1101 with fresh eyes. If Andromeda was a separate galaxy, then surely many of the other nebulae in Herschel's catalogue were galaxies too. Distance measurements became a priority. Astronomers used various techniques to estimate how far away these galaxies were. For relatively nearby galaxies, Cepheid variables worked well. For more distant ones, astronomers looked for the brightest stars or used the overall luminosity of the galaxy to estimate its distance. IC 1101, however, was so far away that even these techniques struggled. It was not until the latter half of the 20th century, with the development of more sophisticated methods and more powerful telescopes, that astronomers were able to determine that IC 1101 sat roughly 1.04 billion light-years from Earth. The light we see from IC 1101 today has been travelling through space for over 1 billion years. When that light began its journey, Earth was still in the Proterozoic eon. Complex animal life had not yet evolved. The most advanced organisms on our planet were simple, single-celled creatures and perhaps some basic multicellular life. Once the distance was known, everything else fell into place. By measuring how large IC 1101 appeared in the sky and knowing its distance, astronomers could calculate its actual physical size. The numbers that emerged were staggering. This was not just another galaxy. This was a monster, something operating on a scale that pushed the boundaries of what seemed possible. From William Herschel's first glimpse of a faint fuzzy blob to our modern understanding of a galaxy spanning millions of light years and containing trillions of stars, the story of IC 1101's discovery spans more than 2 centuries of astronomical progress. It is a story of patient observation, technological innovation, and the gradual accumulation of knowledge. And it is a reminder that sometimes the most important discoveries begin with the most humble observations. The galaxy that refuses to follow the rules. IC 1101 does not just break records, it shatters our assumptions about what galaxies can be. When astronomers first began studying galaxies in detail during the early 20th century, they developed theories about galactic structure and evolution based on what they could observe. Most galaxies fell into recognizable categories. There were spiral galaxies like our Milky Way, with their beautiful pinwheel arms and active star formation. There were elliptical galaxies, smooth and featureless, typically filled with old stars. There were irregular galaxies, chaotic systems often distorted by gravitational interactions. Each type had certain expected properties, certain size ranges, certain stellar populations. IC 1101 takes the category of elliptical galaxy and pushes it to an extreme that forces us to reconsider what we thought we knew. Let us start with the most obvious statistic. IC 1101 measures somewhere between 4 and 6 million light years from one side to the other. The exact number depends on how you define the edge of a galaxy. Galaxies do not have sharp boundaries. They gradually fade into the darkness of intergalactic space, with their outermost stars becoming increasingly sparse until they are indistinguishable from the background. Different measurements using different detection thresholds will give slightly different sizes. But regardless of exactly where you draw the line, IC 1101 is monumentally large. Our Milky Way, by comparison, is about 100,000 light-years across. Even if we are generous and include the very faint outer halo of stars that extends beyond the main disk, we might stretch that to 150,000 or even 200,000 light-years. IC 1101 is still 20 to 40 times larger. To make this comparison more concrete, imagine shrinking the Milky Way down to the size of a dinner plate, about 10 inches across. On that scale, IC 1101 would be the size of a large swimming pool, something like 50 feet across. Our entire galaxy, with all its spiral arms, all its star-forming regions, all its stellar clusters and nebulae, would fit comfortably in the deep end of IC 1101's pool. Or consider it this way. The Andromeda Galaxy, our nearest large galactic neighbour, sits about 2.5 million light-years from the Milky Way. If you placed IC 1101 where our galaxy currently sits, its outer edges would extend past Andromeda's location. The Andromeda Galaxy would find itself inside IC 1101's massive structure. The Triangulum Galaxy, another nearby spiral sitting about 3 million light-years from us, would also be engulfed. All the dozens of dwarf galaxies that orbit the Milky Way and Andromeda would simply become minor components of this giant's outer regions. But size is only part of what makes IC 1101 so remarkable. The number of stars it contains is equally staggering. Current estimates place the stellar population at around 100 trillion stars. That is 100 quadrillion individual stellar objects, each one a fusion reactor, each one potentially hosting planet, each one with its own life story. Our Milky Way contains somewhere between 200 billion and 400 billion stars, depending on which estimate you trust. Let us use the upper end of that range to be generous to our home galaxy. Even at 400 billion stars, IC 1101 has 250 times more stars than the Milky Way. If you could somehow gather 250 galaxies like ours and merge them all together, you would approach the stellar population of IC 1101. The mathematics of counting 100 trillion of anything becomes absurd very quickly. If you counted one star per second without ever stopping, you would need about 3.17 million years to count all the stars in IC 1101. That is longer than anatomically modern humans have existed on Earth. It is longer than the entire genus Homo has existed. You would need to start counting before the first stone tools were invented and continue counting through every moment of human evolution and history just to get through IC 1101 stellar census. Or consider this approach. The human brain can subitize, meaning instantly recognize without counting, up to about 4 or 5 objects. Beyond that, we need to count sequentially. If you looked at IC 1101 stars and tried to count them by eye, even if you could somehow see them all at once, and even if you could count at an impossibly fast rate of 100 stars per second, you would still need more than 31,000 years to finish. IC 1101 sits at the center of a galaxy cluster called Abel 2029, located in the direction of the constellation Virgo as seen from Earth. Galaxy clusters are massive structures, gravitationally bound collections of hundreds or even thousands of galaxies. Abel 2029 contains hundreds of galaxies of various sizes, all orbiting around their common center of mass, and right at the heart of that cluster, dominating everything around it, like a cosmic emperor on a throne, sits IC 1101. Its position is not accidental. The largest galaxy in a cluster almost always sits at the cluster's center because of a process called dynamical friction. As massive objects move through a sea of smaller objects, they experience a drag force that causes them to lose energy and spiral toward the gravitational center. Over billions of years, IC 1101 sank to the bottom of Abel 2029's gravitational well and stayed there, growing larger as other galaxies fell into it. The cluster environment itself is extreme. The space between galaxies in Abel 2029 is not empty. It is filled with extremely hot gas, heated to temperatures of tens of millions of degrees Kelvin by the gravitational energy released as the cluster formed. This intracluster medium is so hot that it glows in X-rays, allowing astronomers to map it with X-ray telescopes like NASA's Chandra Observatory. The total mass of this hot gas is enormous, far exceeding the combined mass of all the stars in all the galaxies in the cluster, and IC 1101 sits at the center of it all, surrounded by this tenuous but massive atmosphere of superheated plasma. Why are these numbers so shocking to astronomers? Because they challenge theoretical models of galaxy formation and evolution. According to our understanding of cosmology, galaxies form from the bottom up. In the early universe, small fluctuations in the density of matter cause some regions to be slightly more dense than others. These overdense regions collapsed under their own gravity, forming the first stars and the first small galaxies. Those small galaxies then merged with each other over time, building progressively larger structures. This hierarchical assembly process, driven by gravity and regulated by various feedback mechanisms, should produce a certain distribution of galaxy sizes. Most galaxies should be relatively small. Intermediate-sized galaxies like the Milky Way should be common, and truly giant galaxies should be rare. IC 1101 sits at the extreme tail of this distribution, pushing right up against theoretical limits for how large a galaxy can grow. Some models of galaxy formation predicted that galaxies could not grow much larger than IC 1101 without running into problems. Gas accretion becomes inefficient at very large masses. Feedback from supermassive black holes can heat gas and prevent it from cooling and forming stars. The expansion of the universe gradually dilutes the density of matter, making new mergers less likely over time. All of these factors should conspire to put an upper limit on galaxy size somewhere in the vicinity of where IC 1101 sits. The fact that we have found such a galaxy is not necessarily surprising, but it is remarkable. IC 1101 represents what happens when every condition is favourable for growth. It formed in an extremely dense region of the early universe. It has had billions of years to accumulate mass through mergers. It sits at the gravitational centre of a rich cluster, ensuring a steady supply of victims to consume. It is, in many ways, the upper limit of what galactic evolution can produce. There is also something profoundly strange about IC 1101 stellar density. Despite containing 100 trillion stars spread across millions of light years, the average density of stars in IC 1101 is actually quite low. The vast majority of the galaxy's volume is empty space, just like in any galaxy. Stars are separated by light years of near vacuum. If you were standing on a planet orbiting a star in the outer regions of IC 1101, your night sky might not look dramatically different from ours. You would see many stars, certainly, but they would still be separated by vast gulfs of darkness. It is only near the centre of IC 1101, in the dense core region, that the stellar density becomes extreme. There, stars are packed so tightly that the night sky would blaze with light from thousands or millions of nearby stars, creating a perpetual twilight with no true darkness. Astronomers who study IC 1101 often express a sense of awe mixed with frustration. The galaxy is so distant that detailed observations are extremely difficult. Individual stars cannot be resolved. The galaxy appears in even our best telescopes as a smooth, diffuse glow. We can measure its overall properties, its size and luminosity and spectrum. We can detect the radio emission from its central black hole. We can observe the X-ray glow of hot gas surrounding it, but we cannot see the detailed structure, cannot map the motions of individual stellar populations, cannot study it with the same level of detail we can apply to nearby galaxies. IC 1101 remains somewhat mysterious despite decades of study, a giant whose full secrets are still partially hidden by distance and the limitations of our technology. And yet, what we have learned is already extraordinary. Building a monster through cosmic cannibalism. IC 1101 did not become the largest galaxy in the known universe by accident. It grew to its monstrous size through billions of years of cosmic violence, consuming other galaxies in a process astronomers call galactic cannibalism. This is not a metaphor or poetic language. IC 1101 has literally eaten other galaxies, stripping away their stars and gas, incorporating all of that material into its own massive body. Scientists estimate that IC 1101 has undergone at least 76 major mergers over its history. That means 76 times another substantial galaxy fell into this cosmic giant and was absorbed. And those are just the major mergers, encounters with galaxies large enough to significantly affect IC 1101 structure. Countless smaller dwarf galaxies have also been consumed, galaxies so small that they barely registered as meals for this enormous predator. To understand how galactic cannibalism works, we need to think about gravity on the larger scales. Galaxies are not isolated objects floating in empty space. They are part of a vast cosmic web, a large-scale structure formed by the gravitational attraction of all the matter in the universe. Dark matter, which makes up about 85% of all matter, forms the scaffolding of this web. Ordinary matter, the stuff that makes up stars and planets and us, follows the gravitational wells created by dark matter, concentrating in dense nodes where the web intersects. These nodes become galaxy clusters, like Abel 2029. Within clusters, galaxies move around each other, their paths determined by the combined gravitational pull of all the matter present. Sometimes galaxies pass by each other at a safe distance, exchanging nothing more than a gravitational tug. But sometimes they venture too close, and when that happens, the interaction becomes violent. The first stage of a galactic merger begins long before the galaxies actually touch. As two galaxies approach each other, their gravitational fields begin to interact. Each galaxy feels a tidal force from the other, stronger on the side facing the approaching galaxy and weaker on the far side. This differential force distorts the galaxies, stretching them along the line connecting their centers. For spiral galaxies, this tidal stretching can be dramatic. The beautiful spiral arms get pulled and warped. Long streamers of stars, called tidal tails, get drawn out from each galaxy, extending for hundreds of thousands of light years into space. These tidal tails are some of the most spectacular structures in astronomy, ghostly ribbons of stars marking the violence of the interaction. When the galaxies make their first close pass, they do not immediately merge. Instead, they swing past each other like dancers, performing an elaborate routine. The gravitational interaction drains energy from their relative motion, slowing them down. They separate again, moving apart to a distance that might be several times their original separation. But now they are gravitationally bound to each other, locked in a mutual embrace from which there is no escape. Over the next few 100 million years, they fall back together for a second pass, then a third, each time getting closer, each time losing more energy to tidal interactions. The process can take 1 billion years or more for large galaxies. But eventually, inevitably, they merge completely, their stellar populations mixing together into a single, larger system. During this merger process, remarkable things happen. The gas in both galaxies, which had been spread out in relatively thin clouds, gets compressed by shock waves and gravitational forces. This compression triggers intense bursts of star formation. New stars light up by the billions, massive blue stars that burn hot and bright. These starburst events can temporarily make a merging system one of the most luminous objects in its region of the universe. Astronomers can detect starburst galaxies billions of light years away because they shine so brilliantly during this brief phase of their evolution. The Hubble Space Telescope has captured stunning images of merging galaxies in various stages of this process, showing the distorted structures, the tidal tails, the brilliant blue knots where new stars are forming in compressed gas clouds. In some mergers, particularly violent ones, gas gets driven all the way to the centers of the galaxies. This gas falls into the supermassive black holes that lurk there, feeding them enormous amounts of material in a short time. The black holes respond by releasing tremendous amounts of energy. The infalling gas forms an accretion disk, a swirling maelstrom of superheated material spiraling toward the event horizon. Friction in this disk heats the gas to millions of degrees, causing it to emit intense radiation across the spectrum from radio waves to X-rays. In extreme cases, the black hole can outshine the entire rest of the galaxy, creating what astronomers call a quasar. Quasars are among the most luminous objects in the universe, visible across billions of light years of space. They are powered by supermassive black holes consuming gas at prodigious rates, and they are often associated with major galaxy mergers. IC1101 has been through this process not once, but at least 76 times. Each major merger brought in hundreds of billions or even trillions of stars. Each merger brought gas that likely triggered bursts of star formation or fed the central black hole. Each merger distorted the galaxy's structure, mixing the stellar populations, destroying any spiral pattern that might have existed. Over billions of years, these repeated mergers transformed IC1101 from whatever it started as into the smooth, elliptical giant we see today. The evidence for this violent history is written throughout the galaxy's structure. When astronomers study the light from different parts of IC1101, they can identify different stellar populations based on their colors and spectra. Some stars are very old, likely members of the original proto-galaxy that existed billions of years ago. Others are younger, formed during merger-triggered starbursts. Still others have chemical signatures indicating they formed in different environments. Foreign stars that originated in other galaxies and were brought to IC1101 as spoils of conquest. Astronomers can also see evidence of past mergers in computer simulations. By setting up virtual galaxies with properties similar to IC 1101 and its neighbours, running the laws of gravity and gas physics forward in time, researchers can watch as the simulated galaxies interact, merge, and evolve. These simulations have become increasingly sophisticated over the years, incorporating not just gravity, but also gas dynamics, star formation, feedback from supernova and black holes, and many other physical processes. When simulations are tuned to match the conditions in the early universe and run forward to the present day, they naturally produce giant elliptical galaxies at the centres of clusters, galaxies that look remarkably similar to IC 1101. This gives us confidence that we understand, at least in broad strokes, how IC 1101 came to be. One of the most fascinating aspects of galactic cannibalism is that it is not a thing of the past. It is happening right now, all across the universe. Our own Milky Way is currently in the process of consuming several smaller galaxies. The Sagittarius dwarf elliptical galaxy is being tidally disrupted and absorbed as we speak, its stars streaming out in a great arc that wraps around the Milky Way. The Canis Major dwarf galaxy is also being torn apart, contributing its stars to our galaxy's disk. In about 4 to 5 billion years, give or take, the Milky Way and the Andromeda galaxy are expected to collide and merge, creating a larger elliptical galaxy that some astronomers have nicknamed Milkomeda. Our own galaxy is participating in the same processes that built IC 1101, just on a much smaller scale. We are witnessing galactic evolution in real time, watching the same cosmic drama play out in our own backyard. IC 1101's position at the centre of Abel 2029 ensured it had an ample supply of merger partners. Galaxies naturally fall toward the densest part of a cluster due to gravity. As they fall inward, they speed up, but they also experience dynamical friction, a drag force caused by gravitational interactions with other galaxies and with dark matter. This friction saps their energy, causing them to spiral ever deeper into the cluster's core. Eventually, they encounter IC 1101, the dominant galaxy sitting at the bottom of the gravitational well. Once they get close enough, IC 1101's enormous gravity captures them. They might orbit for a while, gradually spiraling inward over hundreds of millions of years. But the end is inevitable. They will be shredded by tidal forces, their stars scattered and mixed into IC 1101's vast stellar population, their gas stripped away and consumed. The mechanics of this process depend on the relative sizes of the galaxies involved. When IC 1101 encounters a galaxy of similar size, a major merger, the interaction is complex and chaotic. Both galaxies are significantly distorted. The final product looks different from either of the progenitors. But when IC 1101 encounters a much smaller dwarf galaxy, a minor merger, the process is more one-sided. IC 1101 is barely affected, while the dwarf galaxy is completely destroyed, pulled apart by tidal forces like cotton candy being torn by wind. The dwarf stars end up scattered through IC 1101's halo, forming faint stellar streams that can sometimes be detected as subtle variations in the surface brightness. These streams are the smoking gun evidence of past cannibalism, the remnants of galaxies that no longer exist as coherent entities. The death of spiral arms and the birth of giants. One of the most striking features of IC 1101 is what it lacks. Unlike our Milky Way with its elegant spiral arms, unlike Andromeda with its pinwheel structure, IC 1101 has no spiral pattern at all. It is an elliptical galaxy, which means it appears as a smooth, featureless ellipse of light. The stars in IC 1101 orbit in complex random direction rather than in the orderly rotation of a disk. There are no dust lanes, no bright star-forming regions, no obvious structure beyond a gradual brightening toward the center. This might seem like a deficiency, a lack of beauty compared to the graceful spirals. But the smooth appearance of IC1101 is actually a testament to its violent history. Every time a galaxy merges, the collision destroys spiral structure. The delicate patterns that make spiral galaxies so beautiful cannot survive the gravitational chaos of a major merger. To understand why mergers destroy spiral arms, we need to think about what spiral arms actually are. In a spiral galaxy like the Milky Way, stars orbit around the galactic center in roughly circular paths, all moving in the same direction like cars on a circular racetrack. The spiral arms are not fixed structures. They are density waves, regions where stars and gas bunch up temporarily as they orbit. Think of a traffic jam on a highway. The cars in the jam are not always the same cars. Vehicles enter the jam from behind and leave it ahead, but the jam itself persists as a region of higher density. Spiral arms work the same way. Stars and gas move through them, bunching up and then spreading out again. The arms are regions of higher density that persist over time, but they are not made of the same stuff from moment to moment. These density waves are delicate. They depend on the orderly, organized rotation of the galactic disk. Every star is moving in approximately the same plane, orbiting in approximately the same direction, with velocities that vary smoothly with distance from the center. This organization allows density waves to form and persist. But when two galaxies collide, all of this organization is destroyed. The galaxies are not rotating in the same plane or the same direction. As they merge, stars from each galaxy get flung into new orbits that no longer respect the original orientation of the disks. The orderly circular motion is replaced by chaotic motion in all directions. Some stars end up on orbits that take them far from the galactic center and back. Others orbit in retrograde, moving opposite to the original rotation. The net result is a distribution of stars that is more spherical than disk-like, with no preferred plane of rotation and therefore no possibility of forming spiral density waves. The transformation from spiral to elliptical is not instantaneous. Simulations show that during a major merger, the system goes through a phase of extreme chaos. Tidal tails stream out into space. The cores of the two galaxies orbit around each other, eventually spiraling together. Gas clouds collide and produce brilliant starbursts. The system might temporarily look very irregular, not fitting neatly into any classification. But after about 1 billion years, once the violence has subsided and the stellar orbits have settled down, what remains is typically an elliptical galaxy. The exact shape depends on the properties of the progenitor galaxies and the geometry of the collision, but the loss of spiral structure is universal. You cannot merge two spiral galaxies without destroying their spiral patterns. IC1101, having undergone at least 76 major mergers, has had any original structure erased and re-erased so many times that nothing of its earliest form remains. If IC1101 started as a spiral galaxy billions of years ago, and we have no way of knowing whether it did, that spiral structure was destroyed in its first major merger. Every subsequent merger mixed the stars more thoroughly, randomized the orbits further, ensured that no trace of ordered rotation survived. What we see today is a galaxy that has been through the cosmic blender dozens of times. IC1101, having undergone at least 76 major mergers, has had any original structure erased and re-erased so many times that nothing of its earliest form remains. If IC1101 started as a spiral galaxy billions of years ago, and we have no way of knowing whether it did, that spiral structure was destroyed in its first major merger. Every subsequent merger mixed the stars more thoroughly, randomized the orbits further, ensured that no trace of ordered rotation survived. What we see today is a galaxy that has been through the cosmic blender dozens of times. A galaxy where the stars move in a complex, three-dimensional dance with no simple pattern. The lack of spiral structure has profound implications for star formation in IC1101. In spiral galaxies, star formation happens primarily in the spiral arms. The density waves that create the arms compress gas clouds, triggering gravitational collapse and the birth of new stars. The arms of the Milky Way are traced out by bright young stars and glowing nebulae, regions where star formation is actively occurring. But elliptical galaxies like IC 1101 have little to no ongoing star formation. Part of the reason is the absence of spiral arms and the density waves that trigger star birth. But the more fundamental reason is the absence of gas. Star formation requires cold, dense gas that can collapse under its own gravity. In spiral galaxies, substantial amounts of gas remain in the disk, providing fuel for continued star formation over billions of years. In elliptical galaxies, most of the gas has been consumed. During mergers, gas behaves differently than stars. Stars, despite being gravitationally attracted to each other, almost never actually collide. The distances between stars are so vast that two galaxies can pass through each other with almost no stellar collisions occurring. It is like firing two shotgun blasts of pellets at each other. The pellets are so small and the space between them so large that very few pellets actually hit each other. But gas clouds do collide. When two gas clouds moving at high speed slam into each other, they do not pass through each other like stars do. Instead, they shock and compress, heating up to extreme temperatures. This heating can do several things. In some cases, it compresses the gas enough to trigger star formation, leading to the starburst events I mentioned earlier. But it can also heat the gas so much that it gets blown out of the galaxy entirely, escaping into intergalactic space as a superheated wind. Over multiple mergers, IC 1101 has lost most of its gas. Some of it was turned into stars during merger-triggered starbursts. Some of it was heated by shock waves and expelled from the galaxy. Some of it may have fallen into the central supermassive black hole, where it would have been either consumed or ejected in powerful jets. The net result is a galaxy that has run out of the raw material needed to make new stars. What remains is a population of stars that are almost all old, ancient objects that formed billions of years ago and have been slowly burning through their fuel ever since. IC 1101 is a dying galaxy in this sense, not because its stars are dying right now, but because no new generations are being born to replace the ones that eventually will die. The smooth, featureless appearance of IC 1101 also makes it harder to study than spiral galaxies. In spiral galaxies, astronomers can map the rotation of the disk by measuring the Doppler shifts of gas and stars at different locations. One side of the disk is moving toward us, the other side away, creating a clear velocity pattern that reveals how the galaxy rotates. This rotation curve can be used to measure the galaxy's mass, including the dark matter that dominates on large scales. In elliptical galaxies, there is no simple rotation. The stars are moving in all directions and disentangling their complex motions to infer the underlying mass distribution is far more difficult. Astronomers have to use sophisticated techniques, measuring the velocity dispersion, the spread of velocities in different parts of the galaxy, and comparing that to models to infer the total mass. It works, but it is harder and less direct than the methods that work for spiral galaxies. Despite these challenges, astronomers have learned a great deal about elliptical galaxies, like IC 1101. We know they are the dominant galaxy type in rich clusters. We know they form through mergers. We know they have old stellar populations and little ongoing star formation. We know they host the largest supermassive black holes. And we know they represent the endpoint of galactic evolution in the densest parts of the universe. IC 1101 is the most extreme example of this class, the largest elliptical galaxy we have found, a monument to billions of years of mergers and the gradual accumulation of mass at the bottom of a deep gravitational well. A dying galaxy with no children. For all its size and grandeur, IC 1101 is a dying galaxy. Despite containing 100 trillion stars, it is not forming new ones. The vast majority of its stellar population consists of old stars, red giants, and yellow stars that have already burned through most of their hydrogen fuel. The massive blue stars that once lit up IC1101's early history have long since exploded as supernovae or collapsed into black holes. What remains is a geriatric population of ancient stars slowly fading toward their inevitable ends. This might seem paradoxical. How can the largest galaxy in the known universe be dying? Should not such a massive structure have vast reserves of gas, enormous star-forming regions, a vibrant and ongoing process of stellar birth? The answer reveals something profound about how galaxies evolve and about the relationship between size and vitality in the cosmos. The key to understanding IC1101's current state lies in the gas problem. Star formation requires cold, dense molecular gas. In the cores of giant molecular clouds, where the gas is densest and coldest, gravity can overcome the internal pressure and cause the cloud to collapse. As it collapses, it fragments into smaller pieces, each of which can become a star. This process has been going on in the Milky Way for billions of years and continues today. New stars are forming right now in regions like the Orion Nebula, in the Eagle Nebula's Pillars of Creation, in countless other molecular clouds scattered throughout our galaxy's disk. But IC1101 has almost no cold molecular gas left. The gas that would fuel star formation has been used up, heated beyond the point where it can cool and collapse, or expelled from the galaxy entirely. How did this happen? The answer has multiple parts, each related to IC1101's violent history. First, every merger that IC1101 experienced brought in gas from the merging galaxy. But mergers are violent events. When two galaxies collide, their gas clouds slam into each other at speeds of hundreds of kilometers per second. These collisions shock heat the gas, raising its temperature to millions of degrees. Hot gas expands and exerts pressure outward. If it is heated enough, it can exceed the galaxy's escape velocity and be blown out into intergalactic space. Even if it does not escape entirely, it becomes too hot to collapse and form stars. It sits in the galaxy or in the surrounding cluster as a diffuse, hot atmosphere, contributing to the X-ray emission that astronomers detect, but not providing fuel for star formation. Second, much of the gas that was not heated and expelled was consumed in the merger-triggered starburst events I described earlier. When gas clouds are compressed by shock waves and tidal forces during a merger, they can collapse rapidly, forming stars at a prodigious rate. These starburst galaxies can form hundreds or even thousands of solar masses worth of new stars per year, far exceeding the leisurely pace of a few solar masses per year typical of spiral galaxies like the Milky Way. But this burst of activity uses up gas very quickly. It is like a bonfire compared to the slow, steady burn of star formation in spiral galaxies. The bonfire is bright and impressive, but it consumes its fuel rapidly and then dies down. Third, the supermassive black hole at IC1101's center has played a role in shutting down star formation. When gas falls toward the central regions of a galaxy, some of it gets captured by the black hole. As this gas spirals inward, it forms an accretion disk where friction heats it to extreme temperatures. The hot accretion disk emits intense radiation, and in many cases, it also launches powerful jets of material perpendicular to the disk. These jets can extend for thousands or even millions of light years into space, ploughing through the surrounding gas and heating it. This process, called AGN feedback, active galactic nucleus feedback, injects enormous amounts of energy into the galaxy and its surroundings. The energy heats gas that might otherwise cool and form stars, essentially shutting down star formation. Evidence for this process can be seen in X-ray observations of IC1101, which reveal cavities in the hot gas surrounding the galaxy, bubbles blown by the energy output of the central black hole. The net result of all these processes is a galaxy that has essentially run out of star-forming gas. What little gas remains is either too hot to collapse or is being actively prevented from cooling by energy input from the black hole. IC1101 stellar population is therefore dominated by old stars. Spectroscopic observations reveal that the light from IC1101 is characteristic of red and yellow stars, cool stars that have already evolved off the main sequence where hydrogen is fused in the core. These stars are in the later stages of their lives. Many are red giants, stars that have exhausted the hydrogen in their cores and have expanded to enormous sizes as they burn hydrogen in a shell around an inert helium core. Others are asymptotic giant branch stars, even more evolved objects that are fusing helium in their cores and hydrogen in an outer shell, pulsating and losing mass through stellar winds that will eventually form planetary nebulae. The absence of young, hot blue stars is telling. Blue stars are massive, burning their fuel quickly and living only a few million to a few tens of millions of years before exploding as supernovae. If IC1101 had any significant star formation in the last 100 million years or so, there would be blue stars visible in its spectrum. Their absence tells us that star formation has been essentially shut down for at least that long, and probably much longer. The youngest substantial populations of stars in IC1101 are likely billions of years old, formed during the last major merger events that the galaxy experienced. This situation is common among giant elliptical galaxies in rich clusters. They are often called red and dead because their stellar populations are old and red, and their star formation is dead or nearly so. It is a consequence of their environment and their history. Galaxies in dense cluster environments experience frequent mergers, which heat and expel gas. They are surrounded by hot intracluster medium, which makes it difficult for new cold gas to fall in from the intergalactic medium. And their central black holes, grown massive through mergers, provide a thermostat that prevents any remaining gas from cooling and forming stars. These factors combine to shut down star formation in the largest elliptical galaxies. There is a certain irony to IIC 1101's situation. It is the largest galaxy we have ever found, a cosmic giant that has consumed dozens of other galaxies, accumulating stars and mass over billions of years. And yet, it is dying. It has no children in the sense that it is not creating new stars to carry on after its current population fades. The stars that exist now will continue to shine for billions of years, some for trillions of years in the case of the smallest red dwarfs. But as they gradually burn out, there will be no new generations to replace them. IC1101 is like an ancient empire that has conquered all its neighbours, but has no heirs to inherit its legacy. It is massive, powerful, and utterly magnificent. But it is also approaching the end of its active life, slowly fading into the cosmic night as its stars age and die one by one. This does not mean IC1101 will disappear anytime soon. The timescales involved are staggering. Even the most massive stars in IC1101, if any still exist, will continue to shine for a few more million years. Sun-like stars have lifetimes of around 10 billion years, and many of IC1101 stars are younger than that, having formed in merger-triggered starbursts a few billion years ago. They will continue to shine for billions of years to come, and the smallest red dwarf stars, the most numerous stars in any galaxy, can burn their fuel for trillions of years, far longer than the current age of the universe. IC1101 will remain a luminous galaxy for a very long time by human standards. But on cosmic timescales, its fate is sealed. It is a dying giant, slowly but inexorably fading away. The black hole that devours solar systems. At the very heart of IC 1101, hidden within the galaxy's bright central core, lurks something even more extreme than the galaxy itself. Sitting at the precise centre of this cosmic giant is one of the largest supermassive black holes ever detected, an object containing somewhere between 40 billion and 100 billion times the mass of our Sun. To put that in perspective, the supermassive black hole at the centre of our Milky Way, called Sagittarius A star, contains about 4 million solar masses. The black hole at the centre of the Andromeda galaxy is larger, with perhaps 100 to 200 million solar masses. But the black hole at the centre of IC 1101 is in a completely different category, dwarfing even these enormous objects. It might contain 25,000 times more mass than the black hole at the centre of our entire galaxy. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. They form when matter is compressed into an infinitely dense point called a singularity, surrounded by an event horizon, a boundary beyond which escape becomes impossible. For stellar mass black holes, formed when massive stars collapse at the end of their lives, the event horizon might be a few kilometres across. For the supermassive black holes at the centres of galaxies, the event horizon can be millions or billions of kilometres across. The size of the event horizon, technically called the Schwarzschild radius, is directly proportional to the mass of the black hole. For a black hole containing 50 billion solar masses, a middle estimate for IC 1101 central black hole, the event horizon would have a radius of roughly 150 billion kilometres. To give that number context, consider our solar system. The distance from the Sun to Earth is about 150 million kilometres, defined as 1 astronomical unit, or AU. The distance from the Sun to Neptune, the outermost major planet, is about 30 astronomical units, or roughly 4.5 billion kilometres. The event horizon of IAC 1101's black hole would extend about 1,000 astronomical units from the singularity at its centre, more than 30 times farther out than Neptune's orbit. The entire solar system from the Sun to the Kuiper belt would fit comfortably inside this black hole's event horizon. If you could somehow replace our Sun with IC 1101's black hole, the event horizon would extend well past Pluto, past the Kuiper belt, reaching into the inner regions of the Oort cloud. How did this black hole grow so massive? The answer is intimately connected to IC 1101's history of galactic cannibalism. Every large galaxy has a supermassive black hole at its centre. We do not fully understand how these black holes form initially, but we know they grow by consuming matter and by merging with other black holes. When IC 1101 consumed another galaxy, it also consumed that galaxy's central black hole. The two black holes would eventually find each other and merge, adding their masses together. Over IC 1101's history of at least 76 major mergers, its central black hole has merged with at least 76 other supermassive black holes, each merger adding to its total mass. This is how you build a black hole containing tens of billions of solar masses. The process by which supermassive black holes merge is both fascinating and violent. When two galaxies collide, their central black holes do not immediately merge. They are separated by thousands of light years and surrounded by billions of stars. But as the galaxies merge and their stellar populations mix, the black holes begin to sink toward the center of the combined system through dynamical friction. Over hundreds of millions of years, they spiral inward, getting closer and closer. Eventually, they form a binary system, two supermassive black holes orbiting around each other. At this point, they are separated by perhaps a few light years or less, still a vast distance, but now gravitationally bound to each other in a tight orbit. As the binary black holes orbit, they lose energy by emitting gravitational waves. Gravitational waves are ripples in the fabric of space-time itself, predicted by Einstein's general theory of relativity and first directly detected in 2015 by the LIGO observatories. When massive objects accelerate, they create these ripples, which propagate outward at the speed of light, carrying energy away from the system. For two supermassive black holes orbiting each other, the gravitational wave emission is substantial. As they lose energy, their orbit shrinks. They spiral closer and closer, orbiting faster and faster, emitting stronger and stronger gravitational waves. The final moments before merger are extraordinarily violent. The black holes might be orbiting each other hundreds of times per second, their event horizons nearly touching. The gravitational wave emission reaching a crescendo. When the black holes finally merge, they release an enormous amount of energy in gravitational waves. For two black holes of equal mass containing a few billion solar masses each, the final merger might release the energy equivalent of several solar masses converted entirely into gravitational wave energy, according to Einstein's famous equation E equals mc squared. That is more energy than all the stars in a typical galaxy would emit over the same brief time period. The merger produces a single, larger black hole, typically spinning rapidly due to the orbital angular momentum of the binary. This spin can later drive powerful jets if gas falls into the black hole, channeling energy along the black hole's rotation axis and creating the spectacular radio lobes that astronomers observe in many active galaxies. IC1101 central black hole has experienced dozens of such mergers over its history. Each merger added mass. Each merger likely produced gravitational waves that rippled through the universe. If we had gravitational wave detectors sensitive enough, and if IC1101 were closer, we might have detected some of these ancient mergers. Future space-based gravitational wave observatories, like LISA, planned for launch in the 2030s, will be sensitive to mergers of supermassive black holes in distant galaxies. When LISA comes online, it might detect events similar to the mergers that built IC1101's central black hole, allowing us to study these processes directly, rather than inferring them from observations of the final products. Currently, IC1101 central black hole is relatively quiet. It is not actively consuming large amounts of matter. There is no brilliant accretion disk swirling around it, no quasar outshining the rest of the galaxy. The black hole is there, dominating the gravitational field in the central regions of IC1101, but it is dormant or nearly so. This quiescence is related to the same gas depletion that has shut down star formation in IC1101. Without cold gas flowing toward the galactic center, the black hole has little to eat. Occasionally, a star wanders too close and gets torn apart by tidal forces, providing a brief meal. These tidal disruption events produce flares of radiation as the star's remains are consumed, but they are rare, perhaps one every 10,000 years or so in a typical galaxy. Most of the time, the black hole sits quietly, waiting. There is, however, evidence of past activity. Astronomers have detected a radio source at IC1101 Center, catalogued as PKS 158+059. This radio emission comes from jets of material that were ejected from the vicinity of the black hole at some point in the past, possibly millions of years ago. Even though the jets are no longer being actively powered, the electrons spiraling in magnetic fields within the jets continue to emit radio waves. X-ray observations have also revealed cavities in the hot gas surrounding IC1101, bubbles blown by the energy output of the black hole. These cavities are enormous, millions of light years across, testament to periods when the black hole was much more active than it is today. The energy required to inflate such large bubbles is staggering, equivalent to the total energy output of billions of stars over millions of years. The core that swallowed dwarf galaxies. At the centre of IC 1101 lies a structure that deserves special attention, a core region so massive and so unusual that it challenges our understanding of galactic structure. In 2017, astronomers using data from the Hubble Space Telescope conducted a detailed study of IC 1101's innermost regions and made a remarkable discovery. The galactic core, the bright central region where stellar density is highest, stretches across nearly 14,000 light-years. That measurement alone is extraordinary. For comparison, the entire Large Magellanic Cloud, a dwarf galaxy that orbits the Milky Way and is visible to the naked eye from the southern hemisphere, spans about 14,000 light-years across. IC 1101's core, just the innermost region of this giant galaxy, is as large as an entire dwarf galaxy, and it contains more stars than most complete galaxies in the universe. But what makes IC 1101's core truly unusual is not just its size, but its structure. When astronomers measure the surface brightness of a galaxy, how much light comes from different regions, they typically find that elliptical galaxies have a characteristic profile. The brightness increases smoothly as you move from the outer regions toward the center, following a mathematical relationship that was worked out in the 1960s and 1970s. For most elliptical galaxies, this profile holds quite well. The very center, the core, might deviate slightly from the standard profile, but the deviations are usually minor. IC 1101's core does not follow this pattern. Instead, the central region is oddly faint for its size, containing fewer stars than would be expected based on the galaxy's total mass and structure. This deficit of stars in the core is not a small effect. Astronomers estimate that hundreds of billions of solar masses worth of stars may be missing from IC 1101's innermost regions, scattered outward into the surrounding galaxy, or perhaps ejected entirely. That is more mass than the total stellar mass of many normal galaxies, an enormous amount of material that somehow got removed from the core. The question is how and why this happened. The answer appears to lie in the repeated mergers of supermassive black holes that occurred as IC 1101 grew through galactic cannibalism. This process, called gravitational scouring or core scouring, is one of the most fascinating predictions of theoretical work on galaxy mergers. Here is how gravitational scouring works. When two galaxies merge, their central supermassive black holes eventually sink to the center of the combined system and form a binary, orbiting around each other. At this stage, the black holes are separated by perhaps a light year or a few light years, still a large distance by human standards, but small on galactic scales. As they orbit, they interact gravitationally with stars that pass nearby. Most of these interactions are mild, slightly deflecting the star's trajectory without dramatically changing its orbit. But occasionally, a star passes very close to the binary black holes, close enough that the gravitational interaction is strong. In these close encounters, the star can gain a significant amount of energy, effectively stealing it from the orbital energy of the black hole binary. The result is a gravitational slingshot. The star gets flung outward at high velocity, sometimes fast enough to escape the galaxy entirely, becoming what astronomers call a hypervelocity star, wandering through intergalactic space. The black hole binary, having lost energy to the star, spirals slightly closer together. Over millions of years, as the binary interacts with thousands or millions of stars, this process continues. Stars are continuously ejected from the core region, each ejection bringing the black holes slightly closer. Eventually, the black holes get close enough that gravitational wave emission takes over, and they spiral together rapidly to merge. But by that point, a substantial number of stars have been ejected from the core, creating a region with lower stellar density than expected. Now imagine this process happening not once, but dozens of times. Every major merger that IC 1101 experienced brought in a new supermassive black hole. Each new black hole eventually formed a binary with the central black hole, and each binary ejected stars from the core before merging. Over IC 1101's history of at least 76 major mergers, this scouring process repeated again and again. The cumulative effect was to evacuate an enormous number of stars from the innermost regions of the galaxy, creating the large, faint core that we observe today. The stars that were ejected did not leave the galaxy entirely. Most of them were simply scattered into orbits that take them far from the centre, increasing the stellar density in the outer regions while depleting the core. Evidence for this process comes from several sources. First, the observed core properties of IC 1101 match quite well with predictions from computer simulations of repeated black hole mergers. When researchers simulate the merger history of a galaxy like IC 1101, including the interactions between binary black holes and stars, the simulations naturally produce large cores with stellar deficits similar to what is observed. Second, the relationship between core size and the mass of the central supermassive black hole follows a pattern that is consistent with gravitational scouring. Galaxies with more massive black holes, which presumably experience more mergers, tend to have larger cores with bigger stellar deficits. IC 1101, with one of the most massive black holes known, has one of the largest and most depleted cores. Third, astronomers have directly detected hypervelocity stars in our own galaxy and in nearby galaxies, stars moving so fast that they will eventually escape into intergalactic space. These stars are thought to have been ejected by interactions with the supermassive black hole at the galactic centre or by interactions with a binary black hole system. The existence of hypervelocity stars confirms that the ejection mechanism predicted by gravitational scouring actually happens. Scaling up this process to the repeated mergers experienced by IC 1101, it is entirely plausible that hundreds of billions of solar masses worth of stars could have been ejected from the core over the galaxy's history. There is also an interesting connection between core scouring and the overall structure of elliptical galaxies. Elliptical galaxies come in different subtypes based on their core properties. Some, called core ellipticals, have large, faint cores similar to IC 1101. Others, called power law ellipticals, have brightness profiles that continue to increase steeply all the way into the centre with no flattening. The difference appears to be related to merger history. Core ellipticals, like IC 1101, have experienced many dry mergers between galaxies that have already used up their gas and formed most of their stars. In dry mergers, there is no starburst to replenish stars in the core, so the scouring by binary black holes dominates. Power law ellipticals, on the other hand, may have experienced wet mergers involving gas-rich galaxies. In wet mergers, starbursts can form new stars in the core region, partially compensating for the stars ejected by black hole scouring. IC 1101 is clearly a core elliptical, and an extreme one at that. Its large core and depleted central stellar density indicate a history dominated by dry mergers, consistent with its position in a rich galaxy cluster, where most galaxies have already exhausted their gas supplies. The core itself, stretching 14,000 light-years across, is a monument to billions of years of black hole mergers. Every star in that core region has survived the gravitational chaos of dozens of binary black hole systems. The stars that were less fortunate, those that passed too close to a binary and received a gravitational kick, are now scattered through the outer regions of IC 1101, or perhaps wandering through the Abel 2029 cluster, orphan stars with no galaxy to call home. The 2017 Hubble study that measured IC1101's core was part of a broader survey of the largest elliptical galaxies in the nearby universe. By studying the core properties of many giant ellipticals, astronomers can test theories of galaxy evolution and black hole growth. IC1101, as the largest example in the sample, provides a crucial data point. Its extreme properties, both its enormous size and its massive depleted core, push the boundaries of what galaxy formation models can explain. Understanding IC1101 in detail requires understanding the full range of processes that shape galaxies, from the initial collapse of dark matter halos in the early universe, through the hierarchical assembly of larger structures via mergers, to the feedback effects of supernovae and active galactic nuclei that regulate star formation, and finally to the gravitational dynamics of binary black holes that scour out galactic cores. IC1101 is a cosmic laboratory where all of these processes have operated at their most extreme, creating something truly unique. Light from 1 billion years ago. When astronomers observe IC1101, they are not seeing the galaxy as it exists today. They are seeing it as it was over 1 billion years ago, when the light currently reaching our telescopes first began its journey across the cosmos. This time delay is one of the most profound and often overlooked aspects of astronomy. We are, in a very real sense, time travelers, looking backward into the history of the universe every time we observe a distant object. The light that left IC1101 1.04 billion years ago has been travelling through space ever since, crossing the vast emptiness between galaxies at the fastest speed anything can travel, and only now, finally, is it arriving at Earth. Understanding what this means requires thinking carefully about cosmic distances, the finite speed of light, and the nature of time itself. Light travels at approximately 300,000 kilometers per second, or about 186,000 miles per second. This is the ultimate speed limit in the universe, a fundamental constant of nature that nothing with mass can reach, and nothing, regardless of mass, can exceed. In the vacuum of space, light maintains this speed indefinitely, never slowing down, never speeding up. In 1 year, light travels about 9.46 trillion kilometers, a distance astronomers call a light year. It is not a measure of time despite the name, but a measure of distance, the distance light covers in 1 year of travel. When we say IC1101 is 1.04 billion light years away, we mean that light from IC1101 takes 1.04 billion years to reach us. The distance, in more conventional units, would be about 9.8 billion trillion kilometers, a number so large that it becomes essentially meaningless to human intuition. 1 billion years ago, when the light we now detect from IC1101 first left that galaxy, Earth was a very different place. We were in the Neo-Proterozoic era, the final era of the Proterozoic eon. Complex animal life had not yet evolved. The most advanced organisms on our planet were soft-bodied creatures like early sponges and simple multicellular organisms. The Ediacaran biota, strange frond-like organisms that represent some of the earliest complex multicellular life, were just beginning to appear. The Cambrian explosion, the rapid diversification of animal life that would produce most of the major animal phyla we see today, was still about 60 million years in the future. The planet's atmosphere had only recently achieved oxygen levels high enough to support complex animal life. The continents were configured differently, gathered together in the supercontinent Rodinia, which was in the process of breaking apart. Everything that has happened on Earth since then, every major event in the history of life, happened while light from IC1101 was making its way toward us. The Cambrian explosion occurred. The first fish evolved, then the first land plants, then the first insects and amphibians. The first reptiles appeared, then the first dinosaurs. The dinosaurs dominated the planet for over 160 million years, and then went extinct in a catastrophic asteroid impact 66 million years ago. Mammals, freed from competition with dinosaurs, diversified and spread. Primates evolved, then hominins, then the genus Homo. Anatomically modern humans appeared about 300,000 years ago. We invented agriculture about 10,000 years ago, developed writing about 5,000 years ago, and built the first telescopes about 400 years ago. Every moment of human history, from the first stone tools to the present day, unfolded while ancient photons from IC 1101 were crossing the void. This time, delay fundamentally shapes how we understand the universe. We cannot know what IC 1101 looks like right now, at this very moment. The information about its current state will not reach us for another billion years. Perhaps IC 1101 has experienced additional mergers since the light we see left the galaxy. Perhaps its central black hole went through a period of activity, shining as a quasar for a few million years before settling back into quiescence. Perhaps, though this seems less likely, some catastrophic event has dramatically altered the galaxy. We have no way of knowing. The observable universe is not the universe as it exists now, but the universe as it was at various times in the past, with the most distant objects showing us conditions from the earliest epochs of cosmic history. Astronomers have learned to embrace this limitation and even to exploit it. By observing galaxies at different distances, we are effectively observing galaxies at different points in cosmic time. Nearby galaxies show us what galaxies look like in the relatively recent past, perhaps a few million or a few tens of millions of years ago. Galaxies like IC 1101 at intermediate distances of around 1 billion light-years show us galactic conditions about 1 billion years in the past, and the most distant galaxies observed by powerful telescopes like the James Webb Space Telescope show us galaxies as they existed when the universe was only a few 100 million years old, a tiny fraction of its current age. By comparing galaxies at different distances, astronomers can trace the evolution of galactic populations over cosmic history, watching how star formation rates have changed, how galaxies have grown through mergers, how supermassive black holes have evolved. IC 1101, observed as it was 1 billion years ago, provides a snapshot of a mature, giant elliptical galaxy. The universe 1 billion years ago was not dramatically different from today in terms of overall structure and evolution. The expansion of the universe was continuing, driven by dark energy. Star formation rates across the cosmos had already declined substantially from their peak about 10 billion years ago. Large galaxies had mostly assembled, though mergers continued to build up the very largest systems. IC 1101 itself was probably close to its current size even 1 billion years ago, having already consumed most of its nearby victims. The light we see shows us a galaxy that is old, massive, and relatively quiescent, much as we would expect a galaxy like IC 1101 to be at that point in cosmic history. Measuring the distance to an object as far away as IC 1101 is a significant technical challenge. For relatively nearby objects, astronomers can use parallax, the apparent shift in an object's position as Earth orbits the Sun. This technique works well for stars within a few thousand light years, but beyond that, the parallax angle becomes too small to measure accurately even with the best instruments. For more distant objects, astronomers use a cosmic distance ladder, a series of techniques that build on each other. Cepheid variable stars, which pulsate in brightness with a period related to their intrinsic luminosity, can be used to measure distances to galaxies out to about 100 million light-years. Type 1a supernovae exploding white dwarf stars that all reach roughly the same peak brightness, extend the distance ladder to billions of light years. But for ICE 1101, even these techniques become difficult. The galaxy is so far away that individual Cepheid variables cannot be resolved. Type 1. A supernovae are rare events, and none have been observed in IC 1101 during the time astronomers have been watching. Instead, distance measurements rely primarily on the galaxy's redshift. As the universe expands, light from distant galaxies gets stretched to longer wavelengths, a phenomenon called cosmological redshift. The amount of redshift depends on how much the universe has expanded since the light was emitted, which in turn depends on the distance to the object. By measuring the redshift of spectral lines in IC 1101's light, astronomers can determine how far away it is. The measured redshift corresponds to a distance of about 1.04 billion light-years, though the exact value has some uncertainty and can vary slightly depending on the cosmological model used to convert redshift to distance. The finite speed of light also means that there are parts of the universe we can never see, even in principle. Objects farther than about 46 billion light-years from us, a distance called the particle horizon, are beyond the observable universe. Light from these objects has not had enough time to reach us since the Big Bang. As the universe continues to expand and age, the observable universe will grow larger as light from more distant objects finally reaches us. But there will always be a horizon beyond which we cannot see, a fundamental limit imposed by the age of the universe and the speed of light. IC 1101, at just over a billion light-years away, is well within our observable universe, but it still serves as a reminder that astronomy is always an exercise in looking backward through time. The technology that revealed a giant. The story of how we came to understand IC 1101 is inseparable from the story of how telescope technology has evolved over the past 2 centuries. When William Herschel first spotted IC 1101 in 1790, he was using one of the largest and most sophisticated telescopes of his era. But by modern standards, it was primitive. The mirror was hand-ground and hand-polished, prone to tarnishing and distortion. There was no photography, no spectroscopy, no ability to measure anything beyond the object's position and apparent brightness. What Herschel saw was a faint, fuzzy blob, indistinguishable from thousands of other nebulae scattered across the sky. The transformation from that fuzzy blob to our current understanding of IC 1101 as a cosmic giant containing 100 trillion stars required centuries of technological innovation and represents one of the great achievements of observational astronomy. The first major breakthrough came with the application of photography to astronomy in the mid-19th century. Before photography, all observations had to be made by eye, with astronomers either sketching what they saw or describing it in words. This method had severe limitations. The human eye can only integrate light for a fraction of a second before the image fades, meaning faint objects simply cannot be seen, no matter how long you look. Photographic plates, on the other hand, can accumulate light over hours or even nights, building up images of objects far too faint for the eye to detect. By the late 1800s, astronomical photography had become standard practice, and catalogues like the Index Catalogue that gave IC 1101 its designation were based largely on photographic surveys of the sky. Photography revealed that IC 1101 was larger and more extended than visual observations had suggested, but it still could not determine the object's distance or nature. That required spectroscopy, the technique of spreading light into its component wavelengths to reveal the fingerprints of chemical elements and the motion of the source. In the early 20th century, astronomers like Vesto Slipher began obtaining spectra of spiral nebulae and discovered that almost all of them showed substantial redshifts, indicating they were moving away from us at high speeds. This was the first clue that these nebulae might be extragalactic, located beyond the Milky Way. When Edwin Hubble measured the distance to the Andromeda Nebula in the 1920s using Cepheid variables, confirming it was indeed a separate galaxy, spectroscopy became a crucial tool for studying galaxies. By measuring redshifts, astronomers could estimate distances. By analysing spectral lines, they could determine the chemical composition of stars and the motions of gas within galaxies. The next major advance came with larger telescopes. Bigger mirrors collect more light, allowing fainter objects to be studied and finer details to be resolved. The 100-inch Hooker telescope at Mount Wilson Observatory, completed in 1917, was the largest telescope in the world for several decades and was instrumental in Hubble's discoveries. It was surpassed in 1948 by the 200-inch Hale telescope at Palomar Observatory, which remained the largest telescope in the world until 1993. These large ground-based telescopes pushed the boundaries of what could be observed, revealing ever more distant galaxies and ever fainter details in nearby ones. IC1101, though difficult to study in detail because of its distance, could at least be observed and measured with these instruments. But ground-based telescopes face a fundamental limitation. Earth's atmosphere, while essential for life, is a nightmare for astronomy. The atmosphere absorbs certain wavelengths of light entirely, particularly in the ultraviolet and infrared parts of the spectrum. Even in visible light, where the atmosphere is relatively transparent, the constant motion and turbulence of air causes stars to twinkle and blurs images. This atmospheric seeing limit means that even a perfectly constructed telescope on the ground cannot achieve the theoretical resolution that its size would allow. The solution is to put telescopes in space, above the atmosphere entirely. The Hubble Space Telescope, launched in 1990, revolutionized astronomy. Floating in orbit 540 kilometers above Earth's surface, Hubble can observe with clarity that ground-based telescopes cannot match. Its 2.4-meter mirror is smaller than many ground-based telescopes, but its location above the atmosphere gives it an enormous advantage. Hubble can detect ultraviolet and infrared light that never reaches the ground. It can resolve details limited only by the physics of light diffraction rather than by atmospheric turbulence. Over its 3 decades of operation, Hubble has observed IC1101 multiple times, capturing images that reveal the galaxy's smooth elliptical structure, its bright central core, and its gradual fading into the darkness of space. The 2017 study that measured IAC1101's core size relied heavily on Hubble data, using the telescope's exquisite resolution to trace the distribution of light in the galaxy's innermost regions. Other space telescopes have contributed different pieces of the puzzle. The Chandra X-ray Observatory, launched in 1999, has mapped the hot gas surrounding IC1101, revealing the superheated intracluster medium and the cavities blown by the central black hole's jets. X-ray observations are impossible from the ground because Earth's atmosphere absorbs X-rays completely, a blessing for life on the surface, but a challenge for astronomers. Chandra's observations show IC1101 embedded in a vast cloud of gas heated to tens of millions of degrees Kelvin, glowing brightly in X-rays. The Spitzer Space Telescope, which operated from 2003 to 2020, observed IC1101 in infrared light, detecting the glow of cooler, older stars that dominate the galaxy's stellar population. Each telescope observing at different wavelengths adds another layer to our understanding. Ground-based telescopes have also improved dramatically through the use of adaptive optics, a technique that uses deformable mirrors and computer control to compensate for atmospheric turbulence in real time. Adaptive optic systems measure the distortions caused by the atmosphere many times per second and adjust the shape of a flexible mirror to cancel out those distortions. The result is images nearly as sharp as would be obtained from space. Modern large ground-based telescopes like the 10-metre Keck telescopes in Hawaii and the 4 8.2-metre telescopes of the Very Large Telescope in Chile routinely use adaptive optics to achieve resolution close to the theoretical limit. These instruments can observe IC 1101 in exquisite detail, though they still cannot match Hubble's ultraviolet capabilities or the X-ray vision of Chandra. The future promises even more powerful instruments. The James Webb Space Telescope, launched in December 2021, is the largest and most powerful space telescope ever built. Its 6.5-metre mirror, nearly 3 times the diameter of Hubble's, and its location at the second Lagrange point, 1.5 million kilometres from Earth, give it unprecedented sensitivity, especially in the infrared. Webb can observe IC 1101 and detect details impossible to see with previous instruments, potentially revealing the structure of stellar populations within the galaxy and providing new insights into its history. On the ground, the next generation of extremely large telescopes is under construction. The Giant Magellan Telescope, with an effective aperture of 25.4 metres, and the Extremely Large Telescope, with its 39-metre mirror, will dwarf any existing ground-based facility when they come online later this decade. These giants will be able to study IC 1101 with unprecedented detail, potentially resolving the brightest individual stars in the core region and mapping the kinematics of stellar populations throughout the galaxy. The hot gas prison around IC 1101. IC 1101 does not exist in isolation. The galaxy is surrounded by an ocean of gas so hot that it glows with X-rays, a vast atmosphere that extends for millions of light years in every direction. This intracluster medium, as astronomers call it, is one of the defining features of galaxy clusters, like Abel 2029. The gas is incredibly sparse by terrestrial standards. If you could scoop up a cubic metre of this material, you would find only a handful of atoms, far fewer than in the best vacuum chambers we can create on Earth. But spread across the millions of light years that separate galaxies in the cluster, this tenuous gas adds up to enormous mass, actually exceeding the combined mass of all the stars in all the galaxies. And it is hot, heated to temperatures of 50 to 100 million degrees Kelvin by the gravitational energy released as the cluster formed. The intracluster medium reveals itself through X-ray observations. At such extreme temperatures, the gas emits most of its energy as X-rays rather than visible light. NASA's Chandra X-ray Observatory has mapped this emission in exquisite detail, showing that the hot gas is concentrated around IC 1101 at the cluster's centre. The X-ray image shows a smooth, diffuse glow filling the space between galaxies, with the brightest emission coming from the densest regions near IC 1101. This distribution is not accidental. The hot gas has settled into the gravitational potential well created by all the matter in the cluster, both the visible galaxies and the dark matter that makes up most of the total mass. IC 1101, sitting at the bottom of this well, is effectively submerged in a sea of superheated plasma. The origin of this hot gas lies in the formation and evolution of the galaxy cluster itself. In the early universe, matter was distributed relatively uniformly, with only tiny fluctuations in density. But gravity amplifies these fluctuations. Regions that were slightly denser than average attracted more matter, becoming even denser. Over billions of years, matter flowed along the cosmic web toward the densest nodes, accumulating in protoclusters. As galaxies and dark matter fell toward these concentration points, they accelerated, converting gravitational potential energy into kinetic energy. When this infalling material reached the cluster center and encountered material already there, collisions occurred. Galaxies, being mostly empty space, could pass through each other relatively unscathed. But gas clouds collided and shocked, converting their kinetic energy into thermal energy. The gas heated up to millions of degrees. This shock heating is the primary mechanism that created the hot intracluster medium. Think of it as the cosmic equivalent of friction. When two gas clouds slam into each other at hundreds or thousands of kilometers per second, the collision heats the gas just as friction heats your hands when you rub them together. But the speeds involved in cosmic collisions are so high that the resulting temperatures are extraordinary. The intracluster medium is, in fact, one of the hottest phases of ordinary matter in the universe, exceeded only by the cores of stars and the regions near black hole accretion disks. If you could somehow transport a cubic centimetre of this gas to Earth, maintaining its temperature, it would emit enough energy to power a small city. The hot gas in Abel 2029 is not static. It is constantly being affected by various processes. Gravity pulls it toward the cluster center, trying to compress it. Thermal pressure pushes outward, resisting compression. These forces balance in a state called hydrostatic equilibrium, similar to how Earth's atmosphere balances gravity against pressure. By measuring the distribution of gas density and temperature, astronomers can infer the underlying gravitational potential, which in turn reveals the total mass distribution, including dark matter. Studies of the intracluster medium in Abel 2029 indicate that the cluster contains about 10 to the 15th solar masses, 1,000 trillion times the mass of our Sun, with roughly 80 to 85% in dark matter, 10 to 15% in hot gas, and only a few percent in stars. But this equilibrium is not perfect. The hot gas should, in principle, slowly cool over time. As it emits X-rays, it loses energy. If nothing counteracted this energy loss, the gas would cool, increase in density, and eventually flow toward the cluster center, where it could potentially fuel star formation in the central galaxy. In some galaxy clusters, this cooling flow does occur. Astronomers observe filaments of cooler gas streaming toward the central galaxy, feeding hundreds of solar masses per year of new material. But in Abel 2029 and in many other clusters with giant elliptical galaxies at their centers, this cooling flow appears to be largely shut down. The gas is not cooling as fast as it should, and very little is reaching IC 1101 to fuel star formation. The culprit is IC 1101 central supermassive black hole. Even though the black hole is relatively quiescent now, not actively consuming large amounts of matter, it is not completely dormant. Periodically, gas does fall toward the central regions of IC 1101, and some of this gas gets captured by the black hole. When this happens, the infalling material forms an accretion disk and releases energy, some of which gets channeled into jets that shoot out perpendicular to the disk. These jets plow into the surrounding gas, depositing energy and momentum. The jets do not need to be continuously active to have a significant effect. Even intermittent outbursts occurring every few million or tens of millions of years can inject enough energy into the intracluster medium to prevent it from cooling. Evidence for this process is visible in the X-ray images of Abel 2029. The hot gas around IC 1101 shows cavities, regions of lower X-ray brightness, where the gas has been pushed aside. These cavities are enormous, extending for hundreds of thousands or even millions of light years from IC 1101's center. They mark the paths of past jets, bubbles blown by the energy output of the central black hole. The gas in these cavities is still hot, but it is less dense than the surrounding medium, so it emits fewer X-rays and appears as dark regions in X-ray images. The cavities are not empty. They contain very hot, very low-density plasma and magnetic fields. the remnants of the jets that created them. By studying the size and properties of these cavities, astronomers can estimate how much energy the black hole has injected into the surrounding gas. The numbers are staggering. Creating a cavity millions of light years across requires energies equivalent to billions of supernovae, or the total energy output of all the stars in a large galaxy over millions of years. This energy does not come from the black hole itself. In the sense of the black hole losing mass, black holes only grow. They do not shrink except through the extremely slow process of Hawking radiation. Instead, the energy comes from the gravitational potential energy of gas falling toward the black hole. As gas spirals inward, it releases energy, and some fraction of that energy gets channeled into jets that do work on the surrounding medium. This feedback process is crucial for understanding the evolution of galaxy clusters and the giant elliptical galaxies at their centers. Without feedback from the central black hole, cooling flows would deliver large amounts of gas to the central galaxy, fueling ongoing star formation and potentially making the galaxy much brighter and bluer than observed. The fact that IC 1101 is red and dead, with no significant star formation, indicates that feedback has been effective at preventing gas from cooling and flowing inward. The black hole acts like a thermostat, regulating the temperature of the surrounding gas. When too much gas starts to cool and flow inward, the black hole becomes more active, injecting energy and heating the gas back up. This self-regulating mechanism can persist for billions of years, maintaining the hot intracluster medium in a state where it neither cools rapidly nor heats up excessively. The relationship between supermassive black holes and the hot gas in galaxy clusters is one of the most active areas of research in modern astrophysics. Observations from Chandra and other X-ray telescopes have revealed that most giant elliptical galaxies at the centers of clusters show similar features, cavities in the hot gas created by AGN feedback. Theoretical models and computer simulations have successfully reproduced these features, confirming that the basic mechanism is well understood, but many details remain uncertain. How exactly does the black hole turn on and off? What determines the strength of the jets, and how efficiently they couple to the surrounding gas? How does this feedback evolve over cosmic time as clusters grow and galaxies merge? These questions drive ongoing research, with IC 1101 serving as a prime example of a system where AGN feedback has been operating for billions of years. Abel 2029 and the gravitational well. IC 1101's position at the center of the Abel 2029 galaxy cluster is not a cosmic coincidence. It is instead the inevitable result of physics and billions of years of gravitational evolution. Galaxy clusters are the largest gravitationally bound structures in the universe, assemblages of hundreds or thousands of galaxies held together by their mutual gravity. Abel 2029 is a particularly massive and rich cluster, containing hundreds of member galaxies spread across a region roughly 10 million light-years in diameter. And at the very bottom of the cluster's gravitational well, at the point where the gravitational potential is deepest and the pull toward the center is strongest, sits IC 1101. Understanding why IC 1101 occupies this privileged position requires understanding how galaxy clusters form and evolve, and how the largest galaxies come to dominate their environments. Galaxy clusters form at the nodes of the cosmic web, the large-scale structure of the universe. On the larger scales, matter in the universe is not distributed uniformly. Instead, it forms a web-like pattern with dense filaments connecting nodes where matter is most concentrated. These nodes become galaxy clusters. In the early universe, shortly after the Big Bang, matter was distributed almost uniformly, with only tiny fluctuations in density, variations of perhaps 1 part in 100,000. But gravity is relentless. Regions that were even slightly denser than average had slightly more gravitational pull, attracting matter from their surroundings. This made them denser still, increasing their gravitational pull further. Over hundreds of millions of years, this process of gravitational instability caused the initially tiny fluctuations to grow into substantial structures. The densest regions collapsed first, forming the first galaxies when the universe was only a few 100 million years old. These early galaxies were small by modern standards, containing perhaps a few billion stars each, but they immediately began to cluster together, drawn by their mutual gravity. As more matter flowed along the cosmic web toward these dense nodes, the protoclusters grew. Small galaxies merged to form larger ones. Additional galaxies fell in from the surrounding regions. Over billions of years, these protoclusters evolved into the mature galaxy clusters we observe today. Abel 2029 is the product of this long evolutionary process, a cluster that has been assembling for most of the age of the universe. Within a galaxy cluster, galaxies do not sit still. They orbit around the cluster's center of mass, moving at speeds of hundreds or even thousands of kilometers per second. These motions are driven by the gravitational pull of all the matter in the cluster, both the visible galaxies and the far more massive dark matter component. But as galaxies move through the cluster, they experience a drag force called dynamical friction. This is not friction in the usual sense of surfaces rubbing together. Instead, it is a gravitational effect. As a massive galaxy moves through a sea of smaller galaxies and dark matter, it gravitationally attracts material from behind and repels material ahead. The net effect is a wake of slightly denser material trailing the galaxy, and this wake exerts a gravitational pull that opposes the galaxy's motion, slowing it down. Dynamical friction is stronger for more massive objects and for objects moving through denser environments. A small dwarf galaxy moving through the outskirts of a cluster experiences relatively little dynamical friction, but a massive galaxy moving through the dense central regions experiences substantial drag. Over time, this drag causes the galaxy to lose orbital energy. As it loses energy, its orbit decays, bringing it closer to the cluster center. Eventually, the most massive galaxies in a cluster sink to the center and accumulate there. This is called dynamical friction-driven mass segregation, and it is the primary reason why the most massive galaxies in clusters are almost always found at or near the cluster center. IC 1101 is the most massive galaxy in Abel 2029, and it sits precisely at the cluster's center. This did not happen instantly. IC 1101 probably formed somewhere else in the protocluster billions of years ago. But its large mass meant it experienced strong dynamical friction as it moved through the developing cluster. Over hundreds of millions or billions of years, it gradually sank toward the center, losing orbital energy to interactions with other galaxies and with dark matter. Other massive galaxies in the cluster likely underwent the same process, also sinking toward the center. When these massive galaxies encountered each other near the cluster core, they merged, adding their mass to what would become IC 1101. This process of mass accumulation at the cluster center is self-reinforcing. The more massive IC 1101 becomes, the stronger its gravitational pull, the more likely it is to capture and merge with other galaxies. The cluster environment also affects IC 1101 in other ways. Galaxies in clusters move at high speeds, and when they pass near each other, gravitational interactions can strip away their outer stars and gas. This process, called tidal stripping, is particularly effective at removing material from smaller galaxies as they orbit through the cluster. The stripped material does not disappear. It gets distributed throughout the cluster, forming a diffuse intracluster light, a faint glow of stars that do not belong to any particular galaxy, but instead fill the space between galaxies. IC 1101 benefits from this process. As strip stars and gas settle toward the cluster center, some of it gets incorporated into IC 1101, contributing to the galaxy's growth. Another environmental effect is ram pressure stripping, which removes gas from galaxies as they move through the hot intracluster medium. Imagine a galaxy moving at 1,000 kilometers per second through the tenuous but extensive hot gas that fills the cluster. From the galaxy's perspective, it is experiencing a wind of hot gas pushing against it. This ram pressure can strip away the galaxy's own gas, particularly from the outer regions where the galaxy's gravity is weakest. The stripped gas joins the intracluster medium, leaving the galaxy depleted of the raw material needed for star formation. This process helps explain why many galaxies in clusters are red and dead, like IC 1101. They have been stripped of their gas and cannot form new stars. Abel 2029 is what astronomers call a relaxed cluster, meaning it has settled into a fairly stable configuration. The cluster has not experienced a major merger with another cluster recently, at least not within the past billion years or so. This is evident from the smooth, symmetric distribution of hot gas revealed by X-ray observations. If the cluster had recently merged with another cluster, the gas would show signs of disturbance, shock fronts, or asymmetric distributions. The relaxed state of Abel 2029 suggests that it has had time to settle into equilibrium, with galaxies orbiting in their established paths and the hot gas distributed according to the underlying gravitational potential. This relaxed state is part of what makes Abel 2029 a good laboratory for studying galaxy evolution in cluster environments. The total mass of Abel 2029, including dark matter, galaxies, and hot gas, is approximately 10 to the 15th solar masses. Of this, IC 1101 contains perhaps 100 trillion solar masses in stars, plus additional mass in its dark matter halo. That means IC 1101 alone accounts for a significant fraction of the total stellar mass in the entire cluster, though it is dwarfed by the cluster's dark matter content. The gravitational well created by all this mass is immensely deep. Escape velocity from the cluster's central regions is thousands of kilometers per second. Any galaxy that falls into the cluster and ventures too close to the center will find it almost impossible to escape. It will either remain in a bound orbit, gradually spiraling inward due to dynamical friction, or it will merge with IC 1101 and cease to exist as a separate entity. This gravitational dominance means that IC 1101's future is intimately tied to the future of Abel 2029. As long as the cluster remains bound, IC 1101 will continue to sit at its center. Any galaxies that remain in the cluster will eventually fall toward IC 1101 and be consumed. Over the next tens or hundreds of billions of years, IC 1101 might grow even larger as it consumes the remaining cluster members. But eventually, the expansion of the universe will dilute the cluster, carrying away galaxies that are not tightly bound. The cluster itself might slowly dissolve as the cosmos expands. But that process will take trillions of years, far longer than the current age of the universe. For now, and for the foreseeable cosmic future, IC 1101 sits secure at the center of its gravitational domain, a giant ruling over a realm of hundreds of galaxies. Dark matter's invisible dominion. When astronomers measure the total mass of IC 1101, they find something remarkable and humbling. The 100 trillion stars that make up the galaxy's visible structure, the component we can actually observe with our telescopes, account for only a small fraction of the galaxy's total mass. The rest, perhaps 90% or more, is dark matter, an invisible substance that does not emit, absorb, or reflect light, but makes its presence known through gravity. This dark matter forms a massive halo surrounding the visible galaxy, extending far beyond the outermost stars, perhaps stretching millions of light years into space. Understanding dark matter and its role in IC 1101 is essential to understanding how the galaxy formed, how it has evolved, and why it looks the way it does today. The evidence for dark matter comes from observations of how galaxies rotate and how they move within clusters. In the 1970s, astronomer Vera Rubin conducted detailed studies of spiral galaxies, measuring the rotation speeds of stars and gas at different distances from the galactic center. She expected to find that rotation speeds would decrease with distance, following the predictions of Newton's laws based on the visible matter. Instead, she found that rotation speeds remained roughly constant, or even increased slightly at large distances from the center. This flat rotation curve, as it is called, indicated that there was far more mass in the outer regions of galaxies than could be accounted for by visible stars and gas. The extra mass had to be in some form that did not emit light, dark matter. Similar evidence came from galaxy clusters. When astronomers measured the motions of galaxies within clusters, they found that the galaxies were moving much too fast to be held together by the gravity of visible matter alone. The clusters should have flown apart billions of years ago if visible matter was all that existed, but they had not. Something with mass, but invisible to telescopes, was providing the extra gravity needed to hold clusters together. Additional evidence came from gravitational lensing, the bending of light by massive objects predicted by Einstein's general relativity. Observations showed that galaxy clusters bend light more than the visible matter alone could account for, again indicating the presence of substantial amounts of invisible mass. Today, the evidence for dark matter is overwhelming and comes from multiple independent lines of observation. Dark matter affects the rotation of galaxies, the motions of galaxies in clusters, the bending of light through gravitational lensing, and even the pattern of temperature fluctuations in the cosmic microwave background, the afterglow of the Big Bang. All of these observations point to the same conclusion. There is about 5 times more dark matter in the universe than ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and us. Dark matter makes up roughly 27% of the total energy content of the universe, compared to only about 5% for ordinary matter. The rest, about 68%, is dark energy, an even more mysterious component that drives the accelerating expansion of the universe. What is dark matter made of? This is one of the biggest unsolved questions in physics. We know what it is not. It is not ordinary matter that happens to be dark, like planets or black holes or clouds of cold gas. Observations rule out these possibilities. There is simply not enough of such material to account for the observed dark matter effects. Instead, dark matter appears to be some new type of particle that does not interact with light or with ordinary matter except through gravity. Many physicists believe dark matter consists of weakly interacting massive particles, or WIMPs, hypothetical particles that have mass and gravitational influence, but interact only very weakly with ordinary matter through forces other than gravity. Enormous experiments have been built to try to detect dark matter particles directly. These experiments typically involve large detectors placed deep underground to shield them from cosmic rays and other background radiation. The idea is that dark matter particles are constantly streaming through space, and occasionally one might collide with an atomic nucleus in the detector, producing a tiny flash of light or a small amount of heat that can be measured. Despite decades of searching with increasingly sensitive detectors, no dark matter particles have been conclusively detected. This does not mean dark matter does not exist. It might simply mean that the particles interact even more weakly than expected, making them extraordinarily difficult to detect. For IC 1101, dark matter plays a crucial role in both structure and history. The galaxy sits within a massive dark matter halo that extends far beyond the visible stars. This halo might contain 10 to 100 trillion solar masses of dark matter, dwarfing the stellar mass. The dark matter halo provides the gravitational scaffolding that holds the galaxy together. Without it, the motions of stars in the outer regions of IC 1101 would be too fast, and the galaxy would gradually disperse. The dark matter also played a key role in the galaxy's formation. In the early universe, dark matter collapsed first under gravity, forming halos into which ordinary matter fell. The ordinary matter, compressed and heated by this collapse, formed stars and galaxies. IC 1101's dark matter halo has been growing through mergers just like the visible galaxy, with each merger bringing in not only stars and gas, but also the dark matter halo of the consumed galaxy. Measuring the dark matter content of a distant galaxy like IC 1101 is challenging. For spiral galaxies, astronomers can use rotation curves, measuring how fast gas and stars orbit at different radii, and inferring the mass distribution needed to explain those velocities. But IC 1101 is an elliptical galaxy with no organised rotation. Instead, astronomers must use the velocity dispersion, the spread of velocities among stars in different parts of the galaxy. By measuring how fast stars are moving in random directions, astronomers can infer the strength of the gravitational field holding them in their orbits, and from that deduce the total mass including dark matter. These measurements indicate that IC 1101's total mass, including dark matter, might be 100 trillion solar masses or more, with the dark matter component dominating. The distribution of dark matter around IC 1101 is not uniform. Computer simulations of dark matter halo formation predict that halos should have a characteristic density profile, denser in the centre and gradually becoming more diffuse at larger radii. Observations of IC 1101 and other giant elliptical galaxies are broadly consistent with these predictions, though there are still uncertainties and ongoing debates about the exact shape of the dark matter distribution. Some simulations predict that the very centre of dark matter halos should have a sharp cusp, with density increasing steeply toward the centre. Other models suggest a more gradual core profile. Distinguishing between these possibilities requires very precise measurements of mass distribution in the central regions of galaxies, measurements that are at the limit of current observational capabilities. Dark matter also affects the larger structure of the universe in ways that are relevant to IC 1101. The cosmic web of filaments and nodes that I mentioned earlier is primarily a dark matter structure. Ordinary matter follows the gravitational potential wells created by dark matter, accumulating where dark matter is densest. Abel 2029 sits at a node of the cosmic web where multiple filaments intersect, a location determined by the distribution of dark matter in this region of the universe. IC 1101's position at the centre of Abel. 2029 is ultimately a consequence of dark matter gravity, which created the cluster in the first place and continues to hold it together. Looking to the future, the mystery of dark matter remains one of the most compelling challenges in physics and astronomy. Future experiments might finally detect dark matter particles directly, or they might rule out the WIMP hypothesis and point toward other possibilities like axions or sterile neutrinos. Future telescopes might measure the distribution of dark matter in galaxies like IC 1101 with greater precision, testing theoretical predictions and refining our understanding of how dark matter halos form and evolve. But even without knowing exactly what dark matter is made of, we can already say with confidence that it plays a central role in the cosmos. IC 1101, like every other galaxy, is fundamentally a dark matter structure, a massive halo of invisible matter within which ordinary matter has accumulated to form stars. Understanding IC1101 requires understanding dark matter and vice versa. Stellar archaeology in a dead galaxy. When astronomers study the light from IC1101, they are not just seeing a uniform glow, they are seeing the combined light of 100 trillion individual stars, each with its own properties, its own age, its own history. By carefully analysing the spectrum of light from different parts of the galaxy, astronomers can perform a kind of stellar archaeology, deducing the ages and chemical compositions of different stellar populations and thereby reconstructing the history of star formation in IC1101. This forensic work reveals that IC1101 is not made of a single, uniform population of stars all born at the same time. Instead, it contains multiple distinct populations, layers of stellar history that record the galaxy's violent past of mergers and cannibalism. The key to stellar archaeology is spectroscopy and photometry. Spectroscopy involves spreading light into its component wavelengths and looking for the characteristic absorption or emission lines created by different chemical elements. Different elements absorb light at specific wavelengths, creating dark lines in the spectrum. By identifying which elements are present and in what quantities, astronomers can determine the chemical composition of the stars being observed. Photometry involves measuring the brightness of an object at different wavelengths, typically using filters that select specific ranges of colour. By comparing brightness in different filters, astronomers can determine the colour of stars, which in turn reveals their temperature and age. Old stars and young stars have different properties. Young, massive stars are hot and blue, burning their fuel quickly. They have relatively simple chemical compositions dominated by hydrogen and helium, the primordial elements created in the Big Bang. Older stars have had time to produce heavier elements through nuclear fusion in their cores and through supernova explosions. These heavy elements, which astronomers collectively call metals, regardless of whether they are actually metals in the chemical sense, get incorporated into later generations of stars. So the chemical composition of a star reveals when it formed. Stars with very low metal content, called population 2 stars, formed early in cosmic history when the universe contained few heavy elements. Stars with higher metal content, called population 1 stars, formed more recently after multiple generations of stars had enriched the interstellar medium with heavy elements. IC1101 spectrum shows evidence of multiple stellar populations. The dominant population consists of old, metal-rich stars. These are K-type and M-type stars, cooler and redder than the Sun, which have already evolved off the main sequence where hydrogen is burned in the core. The presence of these stars indicates that most of IC1101's stellar mass formed billions of years ago, during an earlier epoch when the galaxy or its progenitors were actively forming stars. The high metal content suggests that these stars formed from gas that had already been enriched by previous generations of stars, consistent with formation in the relatively recent past rather than in the very early universe. But within this dominant old population, astronomers can identify subpopulations with different properties. Some regions of IC1101 show slightly different colours or spectral features indicating variations in age or chemical composition. These variations are the fossil record of past mergers. When I=C1101 consumed another galaxy, it incorporated that galaxy's stellar population. If the consumed galaxy had a different star formation history, its stars would have different ages and chemical compositions. Over time, as the merged system relaxed and the stellar populations mixed, these differences became more subtle. But careful analysis can still detect them, revealing the complex history of accretion and merger that built IC1101. One particularly interesting feature is the presence of stellar streams and substructure in the outer regions of IC1101. When a satellite galaxy is tidally disrupted and consumed, its stars get pulled into long, thin streams that trace the orbit of the original galaxy. These streams can persist for billions of years, gradually dispersing but remaining detectable with sensitive observations. Hubble Space Telescope images of some giant elliptical galaxies have revealed faint shells and streams in their outer regions, ghosts of past mergers. Similar features probably exist around IC 1101, though detecting them is challenging given the galaxy's distance. Future observations with more powerful telescopes might reveal these subtle structures, providing additional clues to IC 1101's merger history. The chemical composition of stars also reveals information about the conditions under which they formed. Elements like carbon, nitrogen and oxygen are produced in different ratios depending on the mass of stars and the rate of star formation. By measuring these elemental abundances in IC 1101 stars, astronomers can infer that the galaxy experienced intense bursts of star formation in the past, likely triggered by mergers. The high abundances of alpha elements like oxygen and magnesium relative to iron suggest that star formation happened rapidly, on timescales of a few 100 million years, rather than spread out over billions of years. This is consistent with merger-triggered starbursts. Astronomers also look for the signature of the older stars in IC 1101. These ancient objects, formed when the universe was young, would have very low metal content and particular spectral features. Finding such stars would tell us about IC 1101's earliest history, providing a glimpse of the proto-galaxy that existed billions of years ago, before mergers transformed it into the giant we see today. However, detecting individual ancient stars in IC 1101 is impossible with current technology. The galaxy is too distant to resolve individual stars, except perhaps the very brightest supergiants. Instead, astronomers look for the integrated light from populations of ancient stars, a subtle signal that requires careful analysis to extract. One of the challenges in stellar archaeology for elliptical galaxies is that mergers mix stellar populations together. In a spiral galaxy like the Milky Way, stars in the disk maintain relatively organized orbits, and different populations occupy different regions. Young stars are found in the spiral arms, where star formation continues. Old stars populate the central bulge and the stellar halo. This spatial separation makes it easier to study different populations independently. But in elliptical galaxies like IC 1101, the mergers that created them also scrambled the stellar populations. Stars from different progenitor galaxies and different epochs of star formation all orbit together in a complex three-dimensional distribution. Disentangling these populations requires sophisticated statistical techniques and large datasets. Despite these challenges, the picture that emerges from stellar archaeology is clear. IC 1101 formed through the merger of many smaller galaxies over billions of years. The bulk of its stars formed between roughly 10 and 12 billion years ago, during an epoch when the universe was experiencing its peak rate of star formation and galaxy growth. Subsequent mergers added additional stellar populations, some younger and some older, creating the complex mix we observe today. For the last several billion years, star formation in IC 1101 has been essentially shut down, so no new young populations have been added. What we see is a frozen record of the galaxy's active past, a geriatric population of ancient stars gradually fading with no new generations to replace them. Radio lobes and the competition for largest. When discussing the largest galaxies in the universe, a complication arises that requires careful definition of terms. If we measure galaxies by the extent of their visible stars, IC 1101 is indeed one of the largest ever found, spanning 4 to 6 million light-years. But if we include other types of structures associated with galaxies, particularly the enormous radio lobes created by jets from supermassive black holes, then IC1101 is not the record holder. That distinction goes to a galaxy called Alcyoneus, announced in early 2022, which has radio lobes extending an astounding 16 million light-years from end to end. Understanding this distinction and what it tells us about different types of galactic structures helps clarify what makes IC1101 special and what it means to be the largest galaxy. Radio lobes are created by a specific type of activity in some galaxies called radio-loud active galactic nuclei. When gas falls toward a supermassive black hole, some of it forms an accretion disk swirling around the event horizon. Friction in this disk heats the gas to extreme temperatures, and magnetic fields become wound up and amplified by the disk's rotation. In some cases, these magnetic fields channel some of the infalling material into two oppositely directed jets that shoot out perpendicular to the accretion disk. These jets are incredibly powerful, containing particles accelerated to nearly the speed of light and carrying as much energy as millions or billions of supernovae. The jets plough through the surrounding gas, carving out enormous cavities and creating structures called radio lobes. These radio lobes are not made of stars or ordinary galactic matter. They are vast regions, sometimes millions of light-years across, filled with very low-density plasma and strong magnetic fields. The energetic electrons spiraling in these magnetic fields emit synchrotron radiation, particularly at radio wavelengths, which is how the lobes are detected. Radio telescopes can map these lobes in exquisite detail, revealing complex structures including hotspots where the jets impact the surrounding medium, filaments where magnetic fields are particularly strong, and overall morphologies that reflect the history of the jet activity. Alcyoneus, discovered by astronomers using data from the Low-Frequency Array radio telescope in Europe, is an extreme example of this phenomenon. The galaxy itself appears unremarkable in optical images, a modest elliptical galaxy containing about 240 billion solar masses worth of stars. But radio observations reveal enormous lobes extending about 8 million light-years on either side of the galaxy, for a total span of roughly 16 million light-years. This makes Alcyoneus the largest single structure associated with a galaxy ever discovered. The lobes are ancient, formed by jets that were active in the past but have since shut off or weakened substantially. The plasma in the lobes is still emitting radio waves, but it is slowly fading as the electrons lose energy. So why is IC1101, with its 4 to 6 million light-year extent, still considered by many astronomers to be the largest galaxy rather than Alcyoneus? The distinction comes down to what you count as the galaxy itself versus structures created by the galaxy. IC1101's 4 to 6 million light-year measurement refers to the actual body of the galaxy, the distribution of stars and dark matter that are gravitationally bound together. This is what most astronomers mean when they talk about the size of a galaxy. Alcyoneus's radio lobes, while impressive and physically connected to the galaxy through the jets that created them, are not part of the galaxy in this sense. They do not contain significant amounts of stars or mass. They are more like the exhaust or waste products of the central black hole's past activity. To make an analogy, imagine measuring the size of a city. You could measure the area covered by buildings, roads, and infrastructure, which would give you one number. Or you could include the plume of smoke and pollution that the city produces, which might extend hundreds of miles downwind, giving you a much larger number. Most people would agree that the first measurement is more meaningful when talking about the size of the city itself, even though the pollution plume is real and caused by the city. Similarly, when astronomers talk about the largest galaxies, they typically mean the physical extent of the stellar and dark matter components, not the radio lobes or other associated structures. That said, the distinction is not always sharp. IC1101 itself shows evidence of past radio lobe activity. The galaxy is associated with a radio source designated PKS 158 plus 059, indicating that its central black hole was more active in the past. X-ray observations have revealed cavities in the hot gas surrounding IIC 1101, blown by jets from the central black hole. These cavities extend for hundreds of thousands or a few million light-years from the galaxy's centre. They are not as large as Alcyonius's lobes, but they demonstrate that IC 1101's black hole has also created extended structures beyond the stellar body of the galaxy. There are other contenders for the title of largest galaxy, depending on how you define size. Some ultra-diffuse galaxies, which have very low surface brightness and are hard to detect, might have stellar components extending across vast regions. But these galaxies typically contain relatively few stars, just a few billion, spread out over a huge volume. They are large in spatial extent, but not in mass or stellar population. IC 1101 is remarkable because it is large in every sense. It has a huge spatial extent, a massive stellar population, an enormous dark matter halo, and one of the most massive supermassive black holes known. It is a giant in terms of physical size, but also in terms of mass, stellar content, and gravitational influence. The existence of giant radio galaxies like Alcyonius does highlight an important aspect of galactic physics. The supermassive black holes at the centres of galaxies can have effects that extend far beyond the visible galaxy itself. The jets from these black holes pump enormous amounts of energy into the surrounding environment, affecting the distribution and temperature of gas over millions of light years. This feedback can suppress star formation not just in the host galaxy, but in neighbouring galaxies as well. In this sense, the influence of a galaxy extends beyond its visible or even gravitational boundaries. IC 1101, sitting at the centre of the Abel 2029 cluster, influences the evolution of hundreds of other galaxies through both its gravitational pull and the feedback from its central black hole. When future surveys map the radio sky with greater sensitivity and resolution, we will likely discover more giant radio galaxies, some perhaps even larger than Alcyonius. These discoveries will continue to push our understanding of how black hole jets interact with their environments and how galaxies affect the surrounding intergalactic medium. But when it comes to the largest concentrations of stars and dark matter assembled into a single gravitationally bound structure, IC 1101 remains the champion. It is the largest galaxy in the traditional sense, a cosmic giant that has been growing for billions of years and now stands as one of the most massive and impressive objects in the observable universe. The cosmic distance ladder to IC 1101. Measuring the distance to IC 1101, more than a billion light-years away, represents one of the great triumphs of modern astronomy. At such extreme distances, none of the direct methods that work for nearby stars are applicable. We cannot use parallax, the apparent shift in position as Earth orbits the Sun, because the angle is far too small to measure. We cannot send probes or use radar ranging as we do for objects in the solar system. Instead, astronomers rely on a cosmic distance ladder, a series of measurement techniques that build on each other, with each rung calibrated against the previous one, extending our ability to measure distances from nearby stars all the way to the edge of the observable universe. Understanding how this ladder works reveals both the ingenuity of astronomers and the fundamental limitations we face when studying the cosmos. The first rung of the cosmic distance ladder is parallax, which works for stars within a few thousand light-years of Earth. As Earth orbits the Sun, our viewing angle changes by about 2 astronomical units over the course of 6 months. This causes nearby stars to appear to shift position relative to more distant background stars. By measuring the angle of this shift, astronomers can use simple trigonometry to calculate the distance to the star. The smaller the parallax angle, the farther away the star. The Gaia space mission, launched by the European Space Agency, has measured parallaxes for over 1 billion stars with unprecedented precision, creating the most detailed three-dimensional map of the Milky Way ever made. But even Gaia's exquisite measurements cannot detect parallax for objects as distant as IC 1101. The parallax angle would be far smaller than even Gaia can measure. For distances beyond the reach of parallax, astronomers use standard candles, objects with known intrinsic brightness. If you know how bright an object truly is, and you measure how bright it appears from Earth, you can calculate its distance. The apparent brightness decreases with the square of the distance, so an object twice as far away appears 1/4 as bright. The challenge is finding standard candles, objects whose intrinsic brightness can be determined reliably. One of the most important standard candles is a type of star called a Cepheid variable. These are pulsating stars that brighten and dim regularly, with periods ranging from days to months. In the 1910s, astronomer Henrietta Swan Leavitt discovered that the period of a Cepheid's pulsation is directly related to its intrinsic luminosity. Longer period Cepheids are intrinsically brighter than shorter period ones. This period luminosity relationship makes Cepheids extremely useful as distance indicators. By measuring the period of a Cepheid's pulsations, astronomers can determine its intrinsic brightness. By comparing that to its apparent brightness as seen from Earth, they can calculate its distance. Edwin Hubble used this method to measure the distance to the Andromeda galaxy in the 1920s, proving it was far beyond the Milky Way and establishing that the universe contains many galaxies. Modern observations with the Hubble Space Telescope have used Cepheids to measure distances to galaxies out to about 100 million light-years, providing crucial calibrations for the next rung of the distance ladder. But IC 1101, at over 1 billion light-years distance, is far too remote for individual Cepheids to be detected. At such distances, even the brightest stars are impossibly faint. For these extreme distances, astronomers rely on even more luminous standard candles, particularly Type 1 supernovae. These are exploding stars that occur when a white dwarf in a binary system accumulates too much mass from a companion star. When the white dwarf reaches about 1.4 solar masses, called the Chandrasekhar limit, it becomes unstable and detonates in a thermonuclear explosion. Because all Type 1a supernovae have approximately the same mass at the moment of explosion, they all reach approximately the same peak brightness. This makes them excellent standard candles. They are also extremely bright, briefly outshining entire galaxies and visible across billions of light years. Astronomers calibrate the brightness of Type 1 supernovae by observing them in nearby galaxies whose distances are known from Cepheid variables. With this calibration in hand, they can use Type 1a supernovae to measure distances to galaxies billions of light-years away. In the late 1990s, two teams of astronomers used Type 1a supernovae to map the expansion history of the universe and made the shocking discovery that the expansion is accelerating, driven by dark energy. This discovery earned the Nobel Prize in Physics in 2011. Type 1 supernovae are now a standard tool in cosmology, used to measure distances and study the evolution of the universe. For IC 1101, however, even Type 1 supernovae face challenges. Supernovae are rare events, occurring perhaps once per century in a typical galaxy. Catching one in IC 1101 requires monitoring the galaxy over long periods, and there is no guarantee that a supernova will occur during the observation window. Instead, astronomers primarily use the galaxy's redshift to estimate its distance. Redshift is the stretching of light to longer wavelengths caused by the expansion of the universe. As space itself expands, light travelling through it gets stretched, shifting toward the red end of the spectrum. The amount of redshift depends on how much the universe has expanded since the light was emitted, which in turn depends on the distance to the source. Measuring redshift is straightforward. Astronomers take a spectrum of the galaxy, identifying the characteristic absorption lines created by elements like hydrogen, calcium, or magnesium. These lines appear at specific wavelengths in the laboratory, but in the spectrum of a distant galaxy, they are shifted to longer wavelengths. By measuring how much the wavelengths have shifted, astronomers can calculate the redshift, typically denoted by the symbol Z. For IC 1101, the measured redshift is approximately Z equals 0.078, meaning the wavelengths have been stretched by about 7.8%. Converting redshift to distance requires a cosmological model, a set of assumptions about the contents and evolution of the universe. The standard model, called lambda CDM, assumes that the universe contains dark matter, dark energy, and ordinary matter in specific proportions, and that it has been expanding since the Big Bang. Using this model and the measured redshift, astronomers calculate that IC 1101 is about 1.04 billion light-years away. There is some uncertainty in this number because the conversion depends on the cosmological model parameters, like the Hubble constant, which describes the current rate of expansion. Different measurements of the Hubble constant yield slightly different values, leading to ongoing debates in cosmology. But the basic distance to IC 1101, roughly a billion light-years, is well established. The cosmic distance ladder is an elegant solution to a difficult problem, but it has limitations. Each rung depends on calibrations from the previous rung, so errors can accumulate. If the parallax measurements are slightly off, that error propagates to Cepheid distances, which then affects Type 1a supernova calibrations, which in turn affects cosmological distance measurements. Astronomers work hard to minimize these errors through better instruments, more measurements, and careful cross-checks using independent methods. But some uncertainty remains inevitable when measuring distances to objects billions of light-years away. Future missions promise to improve distance measurements. The Nancy Grace Roman Space Telescope, planned for launch later this decade, will observe thousands of Type IR supernovae and measure their properties with high precision, improving the calibration of cosmological distances. New ground-based surveys will monitor millions of galaxies for transient events, like supernovae, increasing the chances of catching them in distant galaxies, like IC 1101. Gravitational wave observations of merging black holes provide an entirely independent distance measurement method, since the strength of the gravitational wave signal depends on distance in a way that can be calculated directly from general relativity. As these new methods develop and mature, our measurements of cosmic distances will become more precise, and our understanding of IC 1101's place in the universe will deepen. Hawking radiation and the black hole's end. Even the supermassive black hole at the centre of IC 1101, the most stable and enduring object in the galaxy, will not last forever. Black holes, despite their name, are not completely black. They emit radiation through a quantum mechanical process discovered by physicist Stephen Hawking in the 1970s, now known as Hawking radiation. This radiation causes black holes to lose mass over time, eventually evaporating completely in a final burst of energy. The timescale for this process is staggering, particularly for massive black holes like IC 1101's 50 billion solar mass monster. But given enough time, trillions upon trillions of years, even this enormous black hole will radiate away into nothingness. Hawking radiation arises from quantum effects near a black hole's event horizon. In quantum field theory, empty space is not truly empty. Instead, it is filled with quantum fluctuations, random variations in energy that cause particle-antiparticle pairs to spontaneously appear and then annihilate each other almost immediately. These virtual particles normally have no observable effect because they exist for such a brief time. But near a black hole's event horizon, something remarkable can happen. If a particle-antiparticle pair appears right at the horizon, one particle might fall into the black hole while the other escapes into space. To an outside observer, it appears as if the black hole has emitted a particle. This emission comes at a cost. The escaping particle carries away energy, and that energy must come from somewhere. It comes from the black hole itself. The black hole loses mass equal to the energy of the emitted particle divided by c², according to Einstein's equation. Over time, this slow leak of particles causes the black hole to shrink. The process is extraordinarily slow for large black holes, but accelerates as the black hole loses mass, because smaller black holes have stronger quantum effects near their event horizons. Eventually, after an unimaginably long time, the black hole evaporates completely, disappearing in a final burst of Hawking radiation. The rate of Hawking radiation depends on the black hole's mass. Larger black holes emit radiation more slowly, and therefore take longer to evaporate. For a black hole with the mass of the Sun, the temperature of the Hawking radiation would be about 60 billionths of a Kelvin, far colder than the cosmic microwave background radiation that currently fills space. Such a black hole would be absorbing more energy from the cosmic background than it radiates, so it would actually grow rather than shrink. Only when the cosmic background has cooled below the Hawking temperature will the black hole begin to lose mass. For a solar mass black hole, the evaporation timescale is about 10 to the 67th power years. IC1101 central black hole, containing about 50 billion solar masses, emits Hawking radiation at an even slower rate. The temperature of its Hawking radiation is about a trillionth of a Kelvin, unimaginably cold. The timescale for this black hole to evaporate is approximately 10 to the 100th power years. That is a Google years, a 1 followed by 100 zeros. To write out this number in full would require more digits than there are atoms in the observable universe. It is a span of time so vast that everything we have discussed so far, from the Big Bang to the death of the last stars, is not even a rounding error by comparison. Let me try to give some perspective on this timescale, though it is truly impossible to comprehend. The current age of the universe is about 10 to the 10th power years. The time until the last stars die is about 10 to the 14th power years. Proton decay, if it occurs, operates on timescales of 10 to the 34th power years. These are all utterly dwarfed by the 10 to the 100th power years required for IC1101's black hole to evaporate. If you took the entire history of the universe from the Big Bang until now and repeated it 10 billion times, you would still have covered only 10 to the 20th power years, a tiny fraction of the time required. If you repeated the universe's history a trillion times, you still would not reach 10 to the 100th power years. As the black hole slowly evaporates, it loses mass, and as it loses mass, the evaporation accelerates. For most of its lifetime, the black hole shrinks imperceptibly slowly. But in the final stages, when it has lost most of its mass and shrunk to perhaps the mass of a mountain, the evaporation becomes rapid. The Hawking radiation intensifies. The black hole glows brighter and hotter, and within a relatively brief period, perhaps a few seconds to a few minutes, it evaporates completely. The final burst releases the remaining mass energy of the black hole as a spray of particles and radiation. What happens to this energy? By the time IC1101's black hole evaporates, the universe will have expanded enormously. Space will be far more dilute than it is today, and any remaining matter will be spread incredibly thin. The energy from the black hole's final evaporation will disperse into this vast, empty space, adding a tiny bit of warmth to the cosmic cold. The particles produced will quickly decay or scatter, contributing to the background of radiation that fills the universe. And then there will be nothing left of the black hole, no remnant, no trace. The object that once contained 50 billion times the mass of the Sun, that shaped the evolution of IC 1101 for billions of years, will be gone. When IC 1101's black hole finally evaporates, about 10 to the 100th power years from now, there will be nothing left of the galaxy at all. The stars will have died trillions of years earlier. The stellar remnants will have decayed away if protons are unstable. The dark matter halo might still exist, but it will be so diffuse and spread out by the expansion of the universe that it barely qualifies as a structure. The black hole's evaporation marks the true final end of IC 1101, the point at which every trace of what was once the largest galaxy in the universe has dissolved into the expanding, cooling void. This far future is almost impossible to imagine. The universe at 10 to the 100th power years will be cold, dark, and unimaginably empty. The temperature of space will have dropped to nearly absolute zero as the expansion continues. The cosmic microwave background will have been stretched to wavelengths measured in light years, effectively disappearing. Any remaining particles will be separated by distances so vast that they might as well be in separate universes. The only events will be the occasional evaporation of a black hole, brief flickers of energy in an otherwise timeless, changeless expanse. This is heat death, the ultimate fate of the universe according to our current understanding, a state of maximum entropy where nothing changes because there is no energy left to drive change. Could 100 trillion stars harbour life? One of the most tantalizing questions about IC 1101 is whether any of its 100 trillion stars harbour life. Given the immense number of stars, the question is not whether life exists in IC 1101. That seems almost inevitable given the numbers involved, but rather how common it might be, what forms it might take, and whether any of it has developed intelligence. This question takes us into the realm of astrobiology and the Drake equation. And while we cannot answer it definitively, we can explore what the numbers suggest and what the implications might be. Let us start with planets. Not every star has planets, but observations from missions like Kepler have shown that planetary systems are quite common. Perhaps 20 to 50% of stars have at least one planet in the habitable zone, the region around a star where temperatures are suitable for liquid water. If we apply this conservatively and assume 20% of IC 1101 stars have planets, that gives us 20 trillion planetary systems. If each system has on average 5 planets, that is 100 trillion planets in IC 1101 alone. Now, not all of these planets will be suitable for life. Many will be gas giants like Jupiter, hostile to life as we know it. Others will be too hot or too cold, too small to hold an atmosphere, or too large and massive. But even if only 1% of these planets are in the habitable zone and have conditions suitable for life, that still gives us 1 trillion potentially habitable planets in IC 1101. 1 trillion worlds where liquid water could exist, where organic chemistry could operate, where life might emerge. How often does life actually arise on a habitable planet? This is the great unknown in astrobiology. On Earth, life appeared quite early, within perhaps a few 100 million years of the planet becoming habitable. This suggests that life might arise readily when conditions are suitable, but we have no other examples to compare. We do not know if Earth is typical or exceptional. If life arises on 1% of habitable planets, IC 1101 would have 10 billion living worlds. If it arises on 1 in a million habitable planets, there would still be 1 million worlds with life in IC 1101. But life and intelligent life are very different things. On Earth, life has existed for about 3.8 billion years, but intelligence capable of building technology and studying the universe has existed for only a few thousand years. The transition from simple life to intelligence required countless steps, each of which might be unlikely. Multicellular life appeared only about 600 million years ago. Animal intelligence evolved only in the last few tens of millions of years. Human-level intelligence is extremely recent. If the emergence of intelligence is rare, there might be billions of worlds with microbial life in IC 1101, but only a few with intelligent civilizations. Let us be optimistic and assume that 1 in a billion planets develops intelligent life. Given 1 trillion potentially habitable planets, that would still mean 1,000 intelligent civilizations in IC 1101. 1,000 worlds where beings have looked up at their skies, wondered about their place in the cosmos, developed science and technology, perhaps built telescopes and spacecraft. This number is, of course, wildly speculative. It could be much higher or much lower, depending on our assumptions. But the sheer number of planets in IC 1101 makes it seem likely that the galaxy is not sterile, that somewhere among those 100 trillion stars, life exists. What would it be like for intelligent beings living in IC 1101? Their night sky would be dramatically different from ours. Near the center of the galaxy, where stellar density is highest, the sky would never be truly dark. Billions of stars would be packed so closely that their combined light would create a perpetual twilight. Astronomers on such a world would have no concept of a dark night sky. They would see stars everywhere, overlapping and blending together, perhaps making it difficult to distinguish individual stars or to navigate by stellar positions. Further out from the center, in regions more like our solar system's position in the Milky Way, the sky might be more familiar. But even there, the sheer number of stars would create a sky far richer than ours. Where we see perhaps a few thousand stars on a clear night, observers in IC 1101 might see tens of thousands or hundreds of thousands, depending on their location within the galaxy. Would intelligent beings in IC 1101 know about the history of their galaxy? Would they have figured out that IC 1101 formed through the merger of many smaller galaxies? That their home is a cannibal giant built on the remains of its victims? If they developed astronomy and studied their galaxy's stellar populations, they might detect the different chemical signatures and ages that reveal the merger history. They might even find stellar streams, the remnants of past merger events. But would they understand the implications? Would they realize that their galaxy is one of the largest in the universe? If they have radio telescopes, and if they are relatively nearby cosmic terms, they might even detect our Milky Way. From IC 1101's perspective, 1.04 billion light-years away, our galaxy would appear as a faint smudge of light, a small spiral among billions of other galaxies visible across the cosmos. If they have instruments comparable to our own, they could study the Milky Way's spectrum, determine its distance, measure its size. But they would be seeing our galaxy as it was 1 billion years ago, long before humans evolved, before even complex animal life existed on Earth. The light currently reaching IC 1101 from our galaxy left when Earth was populated only by simple, single-celled organisms. Communication between civilizations in IC 1101 and civilizations elsewhere in the universe faces enormous challenges. A radio signal from IC 1101 would take over 1 billion years to reach us. If we sent a reply, it would take another 1 billion years to get back. By the time a message made a round trip, more than 2 billion years would have passed. Civilizations rise and fall on far shorter timescales. Even if intelligent life exists in IC 1101 right now, we will not see evidence of it for over 1 billion years, and any signals we might send would not reach them until over 1 billion years in the future. Within IC1101 itself, communication between different civilizations would be constrained by the size of the galaxy. IC1101 spans 4 to 6 million light years. A radio signal from one side to the other would take 4 to 6 million years. Even at the speed of light, the fastest anything can travel. Communication across the galaxy would be a multi-million-year endeavour. This makes any kind of galactic civilization or federation seem impractical. Individual civilizations might arise, flourish, and die out without ever knowing that others exist elsewhere in the galaxy. However, there is one environment in IC1101 where civilizations might have a better chance of detecting each other: the dense central core. In the innermost regions of IC1101, stars are packed much more closely than in our neighbourhood. The average distance between stars might be measured in a few light years, rather than the 4 light years that separate us from our nearest stellar neighbour. In such an environment, interstellar communication would be more feasible. A radio signal would reach neighbouring star systems in just a few years. Multiple civilizations might arise in the same region and actually be able to communicate, forming the kind of galactic community that science fiction often imagines. Of course, all of this is speculation. We have no evidence that life exists anywhere other than Earth. We do not know how common life is, how often intelligence evolves, or how long technological civilizations last. But IC1101, with its 100 trillion stars and perhaps 1 trillion potentially habitable planets, is a tremendous testing ground for these questions. If life is anything more than extremely rare, IC1101 should be teeming with it. The fact that we cannot detect any signs of life from such a distant galaxy tells us nothing. We would not be able to detect even very advanced civilizations at that distance with current technology. But it is fascinating to contemplate that somewhere in that vast collection of stars, on planets orbiting suns we cannot even individually resolve, life might exist, perhaps even looking back at us across the billion light years that separate our galaxies. IC1101, the observed upper limit of galactic scale. IC1101 represents something close to an upper limit, a galaxy so large that few, if any, larger ones will ever be found. It is the product of nearly 14 billion years of cosmic evolution, of countless mergers, of gravity and dark matter, and feedback processes all operating at their most extreme. From a small collection of proto-galaxies in the early universe to the massive dying giant we see today, IC1101's history spans the entire age of the cosmos. Its 100 trillion stars, its supermassive black hole containing tens of billions of solar masses, its position at the centre of a rich galaxy cluster, all of these features mark it as something extraordinary. And yet, for all its immensity, IC1101 is governed by the same physical laws that govern every other object in the universe, from the smallest atom to the largest structure. Gravity, electromagnetism, the strong and weak nuclear forces, these fundamental interactions sculpted IC1101 just as they sculpt everything else. The galaxy is not special in the sense of requiring new physics or exotic processes. It is simply an extreme example of processes that are universal. Understanding IC1101 helps us understand galaxies in general, and understanding galaxies helps us understand the universe as a whole. Perhaps the most remarkable thing about IC1101 is not its size or its mass or its age, but the simple fact that we know it exists. From a small rocky planet orbiting an ordinary star in an unremarkable spiral galaxy over 1 billion light years away, human beings have discovered this cosmic giant. We have measured it, studied it, traced its history, and predicted its future. We have done this using mathematics and physics, tools developed by thousands of people over centuries, refined through countless observations and experiments. IC1101 is a testament to what is possible in the universe, but our knowledge of IC1101 is a testament to what human curiosity and ingenuity can achieve. When you look up at the night sky, IC1101 is there, too faint and too far away for you to see, but there nonetheless, shining with the light of 100 trillion stars. That light has been travelling for over 1 billion years to reach us, ancient photons carrying information about a galaxy as it existed when Earth was young and lifeless. We are fortunate to live in a time when we can observe such objects, when telescopes powerful enough to detect them exist, when our understanding of physics is deep enough to interpret what we see. The universe has been generous in revealing its wonders, and IC1101 is among the most magnificent of those wonders, the largest galaxy we have ever discovered.